But because I mentioned that we want to find a unified representation for all of these machine learning intelligent features, right? So how can we do that? The first thing we have to do is to construct a unified coordinate system. So the way we use is to select a set of anchors inside the space of the latent space. For example, we have 3 anchors here. We have the purple one, the green one, and also the red one. Then if we have a target, another embedding, another vector in the space, we calculate the cosine similarity between these 2 vectors. And then this means we can project this yellow dot into a new coordinate system. Then this 3-dimensional, if we only have 3 anchors here, this is a new 3-dimensional coordinate system that all the models can share because they use the same anchor they project into this unified coordinate system. So one thing that's important is how many anchors we need for the transformation, and also how can we sample these anchors from this latent space. So I used the direct sampling strategy developed by the Shimion's group, and this is the projection of the anchors, which are the blue points, onto the all the chemical space, and this can show the diversity and the coverage of the anchors we selected. Here I selected 100 anchors. So with this kind of transformation and transform all the machine learning potential into this unified coordinate system, the result is quite remarkable. As we can see, almost all the 7 models, they can project into a unified way. So this is the result for the 400 anchors. So this is the previous projection, and now with the anchors, they can project it into a unified way. And so we also tested the robustness of the anchor-based transformation. Like we tested how many anchors we need to achieve this kind of result. So we tested the anchor numbers of 3 anchors, 8, 20, 50, 100, 200, 400. We find very interesting trends is when the anchor number is below 20 or equal to 20, they can still work quite well for the models. Like they can still project them into a unified way. But when we increase the anchor numbers at some intermediate level, like between 15 to 200. So the 2 models, like small model and medium model, they can converge. But for the old models, they appears differently. And then when we increase, after increase the anchor numbers, they can reconverge again. So this divides the anchor region into 3 parts, like the small number of anchor sets, and the intermediate range, and also the very large range. So for the small, medium range of anchors, because the transformation yields only a coarse globally averaged alignment, so there's still alignment there. But in the intermediate range, so because in this range, the mapping is partially constrained, so the underlying diversity of the model representation can emerge from this range. But when the number of anchor sets is quite large, so they become sufficiently constrained to correctly get the local distortions. So this is not only our findings. When I searched the literature, I found that one word they tried to work on the language transformers. They found that so the stars here means the intermediate level. So when the depth of the neural networks is at the intermediate level, they can capture the most diversity of the representations. So the representation can converge toward the brain-like representation. So after we have the unified representation of the force field, what we can do with them. So we think that the platonic representation can enable a lot of invariant cross-model embeddings. So our ultimate goal is to do the model stitching, which is when we have a pre-trained model, like the red model, and we have another pre-trained model, we can just stitch the encode part with the decode part together to get a new model. So the model, we don't have to train anymore because the knowledge are transferable, because they are in the unified coordinate system. So the model can also work. And then they can be applied to different different modality of the problems we try to solve. But here, I will use some materials-related examples to show the power of the unified representation. So I already introduced what is embeddings, and then the important thing here is that without the invariance, the vector of the embeddings, they will change from model to model, right? You train the model, I train the model, we can't directly compare our models. Like I can't take the embedding of King from your model to minus the embedding of men from the other model, right? So making the cross-model comparison impossible. But with invariance, the vector of the embeddings, they stay unchanged from model to model, so they can make the cross-model comparison meaningful. So there are three types of embedding arithmetic we can propose here. One is that we can get the pooled embedding for a material that we are interested in. The second one is by doing the embedding, like the minus the arithmetic between embeddings, we can find the difference of different phases or symmetries of one material. So we can find the symmetry effect on the embeddings. So another thing is, if you care about the reaction, how can we represent a reaction, right? So in this unified way, we can use the embeddings of the products to minus the embedding of the reactants, then we can get the embedding for one reaction. Yes, so let's see some results of them. And before we go to the results, I want to mention that for this comparison, I used the anchor within the intermediate regime, so they can choose some diversity and the model with difference. So I choose 100 anchors here. And we can see that for the three main large medium small model, we can converge quite well. And with the mates and the 7 open models, they are skewed, but still keeps the distribution and the shape. And then with the 2 off models, they kind of skewed more and lost the off-board distribution, which I will call them topology of the distribution that are. So this is the result of the invariant representation for materials, symmetry, and reactions. So the way how I do that is we have one material that we are interested in, so we pool the embeddings together, and here I only show the module of the vector, so the length of the vector. As we can see for the first column, like for the large, medium, and the small models, their modules are quite similar in the length. And also when I compare their similarity to, if I use the small model, the vector from the small model as a reference, so the similarity of them is also quite high. They are almost always above 8.8. And then for the other models, the similarity are also high, but the length of the vectors are varying, so they're different. But as we introduced before, if we have the ideal representation of all the chemical space of the materials, they should be unified to one value, right? So this means that our current state of model training is still not converged to the ideal yet, because the values are still different. But the similarity is kind of high. It's like their directions, the angles are aligned well. So for the symmetry part, for the symmetry, the way how I do it is we have two faces, then we can have the two modules, and then we can see that okay, they're indeed different, right? So the model 1 and model 2 represent the length of the vectors of the two faces. They're different. That's good message because this means the model can differentiate the two different faces. And then I also calculated the two modules similarity. So for the two kind of materials, here they are only the distortion of the octahedron. So the local environment is doesn't change a lot, only the rotation. So that's why the similarity of the two bases, they are very high. But I also want to compare cross model, which means when we get to the difference vector of the two bases, then we reference it to one model. And now there's some divergence here. So this means from model to model, if we want to measure the symmetry difference, then they couldn't converge so well. This means the local arrangement of the vectors in the Latin space is still somewhat different, like their correlation is captured. But this is also something we need to improve in the future. So the last column is about the embeddings for the reaction. So the way how we understand them is we get the reaction and then we get the overall representation of this reaction, and they should converge similar to the single material case, but still like their representation are quite similar if we care about the similarity score. So some takeaway message from this part is the current state of the art models, they can already include certain level of invariance because they tend to be similar. But the true cross-model invariance should preserve exactly the same embedding vectors as well as their models, and their angles should be zero, like the similarity should be close to 1. And then as the physical and chemical information of materials have only one unique truth, right? So the Platonic representation of future trained models, they should converge to one invariant form. So another application we can use the Platonic representation is that we can find that with the Platonic representation, they can still preserve the chemical information. Like if I extract all the element embeddings from the pre-trained models and map them out, so the different colors means different groups of elements. They can cluster quite well, like transition metals or the rare earth metals, or they can follow the trends encoded in the periodic table. And also, like the appearance looks always like unified, except the two models. I will discuss the rate and background and also the consequences of these non-equivariant models. So to quantify the exact cross-model, like their similarity or dissimilarity, I used 4 different measures. One is the KN score. So the KN score denotes that in the embedding space, we use the KN to check the local environment. And we found that the higher the score, the higher the similarity of the models. So the three models from large, medium, and small, they always use very similar behavior. Local environment of the embedding space. And also the 2 op models, they are similar to each other. But when we change the next format or the other models, they are not so similar locally. This means the arrangement of the vectors in the Latin space, they still vary. And then another thing to check is the overall appearance of the topology, of the distribution of the embeddings. So I used the Crocker state score, which is calculated this way, like optimal transport cost, which is when we have two distributions of the embedding space, what is the cost for us to make this embedding space into another, to change it into another embedding space. So this is the cost. And then I have the super scores, which is by the score of the optimal transport divided with the other two scores. So the results are quite constant because for the A and B, we show that the small, medium, and large models, they're always similar, and all models, they cluster themselves. And here, because the scale bar is from above 0.5, and if I use another scheme, this means all models from the distribution level, they are all quite similar. And then for the cost, so the lower cost means we don't have to change much from one embedding mapping to another. So the blue color means lower cost. So for the 3 large, medium, and small models, the cost is low. But for the cost that if we want to change the mass large model to the Z-O model, they can cost a larger cost here. Yes. So this can give us some metrics and quantified metrics to measure the similarity and the dissimilarity of the learned Platonic representation. So another use case for this Platonic representation is to track the fine-tuned dynamics. People might be familiar with the maze fine-tuning scheme. So before the multi-head training scheme, we have the naive fine-tuning, which is we have the data, and then we apply the data to the maze model, the base model. This is the original name of the 3 maze models, the medium model, small model, and the DLB model. The DLB model has more information about the repulsion parts of the 2 atoms. So here we want to check if we can fine-tune the medium model to have the capability to capture the copper-copper dimer interaction correctly. As shown by this blue curve here, if there's no fine-tuning, the mass medium model, they couldn't predict well at the short distance of the dimer interaction. They failed. That's why we need to fine-tune the model with the capability of the DLB models, because DLB models is intended to capture this kind of a repulsion part. But with the naive fine-tuning scheme, then all the other information are lost, so all the embeddings vanish. So the only information is the information we get to the fine-tuning model. So this means that the model couldn't generalize to another system because they lost every previous information. And we tested the goat-goat dimer interaction, which is not presented in the fine-tuned dataset. And then with the naive scheme, and then using the fine-tuned model, we try to predict the dimer-dimer interaction of goat, and then the green color shows here, they deviate from either the target DLB model or the original media model. This is not physically meaningful result. So the current scheme for fine-tuning is the multi-head one. So as we can see here, so all the models, they can preserve a unified representation, and also they didn't, the embeddings of the other information doesn't vanish, and also the new information was added on to this fine-tuned model. So they can do well for the copper-copper dimer, and for this goat-goat dimer because they are flat-tuning representation. So the last point I want to make is, because as I mentioned, the op models, they are non-equivalent models. Equivalent means that when we have the structure, so we need to make them, if we rotate them, the representation shouldn't change, or the value, like the module I calculated before, shouldn't change. Or if we permutate some the sequence of the representation, and another one, I don't remember. Yeah, there are three equivalent quantities here. So, but for the training of the op models, they didn't enforce these equivalence. So they don't use the physically informed way to encode the equivalence. They only use some loss function to say that if we rotate a little bit, we punish that rotation. And then, so they taught that equigrade scheme. But after I checked the representations of the original structure of this material with the rotated structure, for the two op models, they couldn't predict their original embedding values. This means they are not invariant to the rotation. But however, for the mass models or the 7 metal or 7 OMAD models, because they are equivalent, so the two sets of structures, the original one and the rotated one, they are actually still the same. So they appear the same as they values. Another result I found that is for the mass models, because for this structure, it's P and MA symmetry. So this means for the different ions in the lattice, they are symmetrically related. So in this structure, we can recognize only one side of the barium and one side of the cerium, and then one side of the oxide. But for the mass models, because they are not equivalent, and also so they couldn't recognize that actually all the oxygens are equivalent to each other, but they give different representations for all of these equivalent ions in the structure. So this will have a big consequence in predicting the local environment sensitive results, for example, the phonon structures, because phonon is very sensitive to the local environment, the forces, right? So if they couldn't predict the correct positions of the atoms, so the phonons will dispute. This is somewhat better result, but still we can see as the gamma points from the two op models, they didn't reproduce. This is the DST result. This is the mass OMAD predictor result. They're almost the same. But for the op models, at the high frequency range, they lost the information, not so predicted so well. And even for the gamma points, they are not predicted so well. And also some fine details inside the phonon results. Because phonon is quite important for a lot of materials properties we care about. So this means non-equivalent models, they do have some severe consequences in our use of the force field. So I hope I have convinced you that platonic representation is useful and is there, and we need to go for that. So the preprint of this work is out next week. So if you are interested, you can find after I upload it. And then, so to conclude, so our current status of the pre-trained machine learning force field models, they are still not at the ideal regime, no matter how high accuracy they claim in the next bench. Yeah, so they're still different. And then the platonic representation provides a unified latent space in which the underlying chemical and physical relationships between materials can be transferred and manipulated. We can do the arithmetic. And also another thing I'm trying to do is that when we have the pre-trained representations in their platonic representation form, so we can easily align the embeddings in this platonic space. So we can reuse the pre-trained models, and we don't have to retrain them from scratch, because for training them force field from scratch is quite expensive. For example, for the native training or the maze training, they use millions of GPU hours, right? So if we can have this kind of representation, we can just stitch them together. Yep, thank you very much for your attention. And, that's a very good question. So, because I think we are approaching the truth of the world, but we can never reach. That means if you have some new cases, perhaps fine-tuning is always needed. But if the model is powerful enough, for example, here there are a lot of big databases, they are here only and big trade, like the models. MPA, maze MPA models, they are trained on this large database, so they can capture more information, so they can be accurate on your cases, but if not, fine-tune is needed.
Thank you for that talk, and I'm curious about your idea. So, is there are you motivated to which so let's say we pre-train some architecture in some database, and is your idea to transfer these data space architecture into different models? So I have one question to the pre-train case. I'm curious, can you give us your motivation to do this?
Yeah, sure. So I don't have a perfect slide for that, but I do have one. We can use this one. So for all of these machine learned interatomic potentials, they depend on different architectures, like how the neural network, the message passing, how the node features, different features are like intact and collected the information. So yeah, this is the architecture part, and also they are trained with different database, like the OMAT, the MP Trash, the Alexandria database, and also different size of the database. So this means that the randomness of all these trained models, that their embeddings are located inside like one architecture, right? Like one model, we can extract one set of embeddings. But my idea is only to add on one layer at the end of this kind of transformation. So for all the trains, we don't have to change the core architectures. We only add one layer at the end to transform the embeddings into one unified coordinate system within the anchor strategy. Then everything, like all the embeddings from all of these models, they can project it into one space. Like we always have one unified x, y, z coordinate. So all the embeddings are in this space. So in this way, we can compare them and we can combine the information and the model stitching.
And I have
Yeah, sure. I think so. So currently, my claim is that all the embeddings after transfer and the embedding for hydrogen atom should be the same, because the chemical information of hydrogen in the whole kind of chemical space of materials should be the same, right? Similar idea is like king always means king, king always means king. So this kind of thing will change. But if we do have some scheme, like one embedding is trained on one modality of they are trying to predict the band gap, let's say, in terms of wireless thinking. And then another model is trained on another protein. So they should have different representations, but we can combine the two representations together. So they can have the power of the two predictors.
And do you believe we can do that without any further continuing?
So this is already realized in the image models. So people can use this kind of stitching ways of different image models trained. Then they can, so one example is for image, we have the image right, input, and we can also have a text to describe this image. So this is different modality of the input data. So we train the two models, and then we transform the embeddings into one space. So the two embeddings are actually comparable, and also they can be put together. Yeah, so they have the ability to be both image part and also the text part.
Any further questions for attention? If there's no question, let's thank Andrew again. Our next speaker for the session will be Nicole Bella from Kyoto University. We're going to talk about the nuclear electrons on post-transition ions.
Hello, I'm Handel Rowan. So first, thank you, Jay, for inviting us. Actually, this is the first time for me to come to Korea, so I'm very excited. So today I'm going to talk about long pairs in materials and its relation between electronic and crystal structure and dynamics. So first I'm going to introduce my university, Kyoto University. This is Kyoto, and this is Tokyo, and this is Fukuoka. So from Kyoto to come here, it only takes 1.5 hours. It's very near. And from Kyoto to Tokyo, it almost takes like 3 hours. So it's much easier to come here rather than to go to Tokyo. So it's very nice. So this is the map of Kyoto, and this is Kyoto Station, and the Kyoto city is like kind of mesh structure because this is ancient capital of Japan. And this is Kyoto Station, and we have Kyoto University. This is the main campus of Kyoto University around here. And my house is here, and I usually commute by bicycle as usual. And it takes like 25 minutes by bicycle from here to here. And this is the city of Kyoto. So my house is kind of in the city. So if you come to Kyoto, you can visit my house. 2 months ago, Sean and his girlfriend visited us and spent one night in our house. So yeah. So please come to Kyoto. So Kyoto University is famous for the unique character, and we have the unique student, unique professors. We respect freedom of student, freedom of research. So this is why we have the highest Nobel Prize winner in Japan. For example, this year we have Nobel Prize in chemistry, and Susumu Kitagawa won Nobel Prize for his study about meteorologic frameworks. We also have Shimon Sakaguchi, who is in Osaka University now, but he got PhD in Kyoto University. So we have like very unique characters in university. So I'm going to introduce myself a bit. I got PhD about study photocatalysis in Kyoto University. So I did experiment when I was a student under the supervision of Professor Ryu Abe. But after getting PhD, I moved to London with Aaron Walsh to learn the DFT. So after 2 years in London, I moved to Tokyo and joined the OVAT group. So before and during student, I did the experiment, but after getting during the postdoc, I did DFT. So it's kind of like, and from this April, I moved to Kyoto University again, and I trying to mixing the experiment and DFT now. So and I'm an assistant professor at Kyoto University. So my study during my PhD is about photocatalysts. So I did a lot of experiments about these systems. In these systems, we employ the semiconductor particles. Under sunlight, we can get electrons and holes in these particles, and these electrons and holes can split water to hydrogen or oxygen. And this hydrogen can be used as energy, green energy. So, for example, So, for example, I developed new materials to use this photocatalyst, and I also developed new synthetic method because in photocatalytic system, the shape and the size of the particle is very important to determine the efficiency. So I also did some study about carrier dynamics and surface modification of materials. But during my PhD, during my postdoc, in Aaron's group, I did mainly 3 studies. First one is about lone pairs on post-transition cations. The second one is a defect in strontium titanate photocatalyst. And the third one is like macroscopic view of materials to understand the electron structures. So all this study is based on DFT. So today I'm going to talk about this first topic, lone pairs. So lone pairs on post-transition cation is very interesting for me. For example, in 2+, the 2+ antimony 3+ between 3+ has NS2 and P0 electron configuration, and these 2 electrons is called lone pairs. Because of these lone pairs, these materials have unique electronic and crystal structures. The materials containing lone pair can be found in everywhere. For example, like perovskite. I think Shah and Younger is very professional about these materials. And lead, this material contains lead 2+. The 2+ has 6s260 electron configuration, and these 2 electrons is lone pairs. The orbital interaction between the 2+ and iodine 5p orbitals provide a unique electronic structure of these materials, which provide, for example, defect tolerance of these materials. Another example in photovoltaics is thin antimony selenide, antimony sulfide, and this structure, the lone pair of antimony provide a unique crystal structure as shown here. This is from Schumann's paper. And we also had like unique materials in photocatalysis like bismuth vanadate and this layered structure. This is my favorite structure. Not only like solar energy conversion systems, we have lone pair materials in thermal electronics. For example, bismuth telluride, lead telluride, and germanium telluride. In these materials, lone pair is reported in these materials. The dynamics of lone pairs is related to the thermoelectrics, and researchers say that the laddering of lone pair is key to provide low thermal conductivity. So another example is ferroelectrics. Now we have these materials where the distortion by lone pair is a key for the ferroelectrics. Not only in these materials, we also have negative thermal expansion because of the lone pair and ionic conductors. And it is also reported that the existence of lone pair in materials provide good ionic conductors in materials. In these materials, for example, oxide ion conductors and fluoride ion conductors in the materials. So lone pair is widely spread in materials. So I think the understanding of lone pair can be a key to control the material, control the electronic structure of these materials. So today I'm going to talk about lone pairs. First, I'm going to introduce lone pair a little bit. I think you are very familiar with lone pair in molecules. For example, we have lone pair in ammonia and water here. Lone pair is kind of defined as a pair of valence electrons that are not shared with another atoms. They are stereochemically active and acting as steric hindrance in molecules like this. So this lone pair can be understood by the molecular orbital interactions. For example, in ammonia case, we have 3 hydrogen and 1 nitrogen. So we can think the interaction between first we can construct circs. Circ is symmetry adaptive linear combination of molecular elementary orbitals. So we can construct 3 orbitals from 3 hydrogen 1 s orbitals as shown here. So and we can construct a molecular orbital with this hydrogen orbitals with a nitrogen orbital as shown here. So the key is the symmetry of the orbitals. See? And the symmetry is key to understand these orbitals. So only the same symmetry can interact with each other. For example, in this case, the hydrogen 3, this A1 orbital can interact with this nitrogen A1 symmetry orbitals as shown here. So on this one orbital and this one 2pz A1 orbitals and this 2s A1 orbitals provide from this A1 molecular orbital shown here. So from 3 bonding, we can get 3 molecular orbitals shown here. And another 2 orbitals represented by E. This also can interact with this 2p Y 2pz on nitrogen which is represented by E. And this from 4 elementary orbital, we can get 4 molecular orbitals. This one and this one. And this is a hormone of ammonia molecules, and this is the room of ammonia molecule orbitals. And electron pairs up to these orbitals, and this is called the lone pairs. So this can be simplified like this. First, we can think about the orbital interaction between 3 hydrogen and 1 2s nitrogen orbitals to produce bonding and anti-bonding orbitals. And these anti-bonding orbitals can further interact with nitrogen 2pz to provide bonding and anti-bonding orbitals here. So, and this is a lone pair. So the key of the lone pair is the contribution of this nitrogen 2pz to the home orbitals here. This because 2pz have a kind of asymmetric electron density. The contribution of p orbitals to home will provide the asymmetric electronic density around the ammonia. So in previous slide, I said lone pair is the electron that are not shared with another atoms, but from this molecular orbital view, the lone pair shared with another atom. I mean, in this case, nitrogen and hydrogen. But this orbital usually kind of localized on nitrogen, so this is called lone pair. So this orbital interaction can understand as a second order Young-Taylor distortions. So the right hand case is distorted case. If the nitrogen molecule is distorted like this, we can this nitrogen 2pz can contribute to the valence band action here. But what happens if the nitrogen is coordinated by hydrogen like this on the same plane? In this case, antibonding combination between nitrogen 2s and hydrogen 1s can be described like this, and this orbital cannot interact with this nitrogen 2pz because the symmetry is different. So in this case, the HOMO is from only this molecules, and there is no bonding between nitrogen 2pz and this hydrogen 1s orbitals. So in this case, this orbital is not stabilized by the nitrogen 2pz. So, but with distortion, this orbital is stabilized by this nitrogen 2pz. So in ammonia, the distortion induces the mixing of the orbital of this nitrogen 2pz and hydrogen 1s. So this is explained from the second Young-Taylor distortion. So we also have lone pair in inorganic material crystals. For example, in tin 2+, lead 2+, antimony 3+, and bismuth 3+. They have two NS2 and pZ configurations, and 2 electrons is called lone pairs. So because of these lone pairs, we have unique crystal structure of the materials. For example, this is the crystal structure of lead oxide. We can find that the coordination environment of lead is kind of distorted. This is because the existence of lone pairs around lead, as shown here. So we have another unique crystal structure. So the origin of this lone pair is also can be considered as orbital interactions. First, we can think let's think about the bismuth is coordinated by oxygen like this. First, we can think about the orbital interaction between oxygen 2p and bismuth 6s to provide a bonding antibonding orbital like this. And this antibonding orbital can interact with empty bismuth 6p orbitals to produce bonding and antibonding orbital, as shown here. In this case, electrons fill these orbitals, and this is asymmetric electron density, which is called lone pairs. So as in the ammonia case, this contribution of bismuth 6p orbitals to the valence band is imported. In ammonia case, this orbital is HOMO and this orbital is LUMO, but in crystals, this is called valence band maximum and this is called conduction band minimum. So lone pair is an electron on the valence band maximum, and in this case, the 6p bismuth 6p can contribute to the valence band, which provides the asymmetric electron density, which is called lone pairs. So the key is the contribution of this bismuth 6p orbitals to the valence band. So I think the second Young-Taylor distortion in ammonia, we can think about the effect of symmetry of coordination environment. So if the bismuth is coordinated by oxygen like this is kind of distorted crystal structure. This bismuth 6s can interact with this antibonding between bismuth 6s and oxygen 2p because of the symmetry. So in this case, the lone pairs are active. And the energy difference between this valence band maximum and the conduction band minimum is called band gap. So what happens if the bismuth is coordinated like this in more high symmetric case? In this case, as in the ammonia case, this bismuth 6s and oxygen 2p orbital 2p combination cannot interact with this bismuth 6s because of the symmetry are different. So if we draw overlap of this material of this orbital and these orbitals, the interaction between bonding and antibonding is the same, so which means there is no bonding with each other. So in this case, this valence band, this bismuth 6p cannot contribute to the valence band. So in this case, the lone pair is inactive. So in this case, the band gap can be energy gap between these orbitals. So in terms of energy, the distorted structure is stable because this orbital is stabilized by bismuth xp. But if we focus on band gap, the right-hand side case has a smaller band gap as compared to the left case. So my hypothesis is if we can control the symmetry of bismuth coordination environment from here to here, we can narrow the band gap of the materials. So this is my hypothesis. So if we can achieve that this kind of the coordination environment, and somehow we can narrow the band gap of the materials. So I try to confining bismuth lone pairs at a high symmetric site. This is my strategy. So I focus on elemental substitution, especially yttrium 3+, because yttrium 3+ doesn't have a lone pair. So you can find yttrium 3+ at high symmetric site more easily than bismuth 3+. So if we can find a high symmetric yttrium 3+ site and we can introduce bismuth 3+ to that site, we can achieve a high symmetric bismuth 3+ that can narrow the band gap of the materials. So I investigate the yttrium 3+ site in all the yttrium oxygen compound in materials project by using KMM Python packages. So this is the singled out structures Bi2 yttrium 4 Cl. And this material already contains bismuth 3+, but if we focus on yttrium 3+, it has almost a perfect cubic environment. So if we can introduce bismuth 3+ to this site, we can achieve an unusual bismuth 3+ site. So first, I investigated. So I analyzed the effect of bismuth substitution using the UFT. When this site is yttrium, band gap is about 1.4. But if we introduce this bismuth, this yttrium, if we replace this yttrium site with bismuth, band gap is significantly narrowed as we had expected from the orbital interactions. So let's take a look at the details. If this site is yttrium, this lone pair active bismuth is contribute to the valence band. So you can see here that bismuth 6p contribute to the valence band. And in this case, lone pair is active. So this is because in the distorted coordination environment, bismuth 6p can contribute to the valence band. So in this case, lone pair can be active, and we can see the bismuth 6p contribution of the valence band. But yeah, and the orbital interaction can be confirmed by using shear chip analysis. In this case, bismuth 6s and oxygen 2p is anti-bonding, and oxygen 2p and the bismuth 6p is bonding, as shown here. So when we introduce bismuth to this site, this bismuth mainly contributes to the valence band, as shown here. So in this case, lone pair is inactive. This is consistent with these orbital interactions. If bismuth is at high symmetric site like this, and this is kind of high symmetric site, this bismuth 6p cannot contribute to the valence band because of symmetry. So we can see only the bismuth 6s contribution to the valence band. So here we have only bismuth 6s contribution on the valence band. The orbital interaction is also again confirmed by shear chip analysis. In this case, bismuth 6s and oxygen 2p are anti-bonding, and bismuth 6p and oxygen 2p is non-bonding, as shown here. So from these results, if we can introduce bismuth to this site, we can narrow the band gap because of the changing of the orbital interactions. So this is experimentally validated. So I synthesized these materials, Bi2 yttrium 1 minus x, bismuth x, or 4x. And this x means that the amount of bismuth on yttrium site. So we introduce bismuth to this site using solid state reaction. So this is a result. We can introduce bismuth to the yttrium site up to x equals 0.4. But above x equals 0.4, this impurity phase is formed because of the stability of the distorted, because this site prefers distorted structure. The bismuth substitution on yttrium site is further supported by hard stem image. This is the stem image, and this point represents 1 atoms. And this is the yttrium layer. And when x equals 0, there is no bismuth peak on the yttrium layer. But if we increase the x, we see the small bismuth peak on yttrium layer, which shows the bismuth is introduced on this yttrium layer. The band gap narrowing is also compounded by experimentally. By introducing bismuth to this yttrium site, band gap is significantly narrowed as shown here. So this is because when there is no bismuth on this site, this lone pair active bismuth contributes to the valence band, where this antibonding combination between bismuth 6s and oxygen 2p is stabilized by bismuth 6p. But if we introduce this bismuth to this site, at high symmetric site, in this site the bismuth 6s and the oxygen 2p antibonding combination is not stabilized by this bismuth 6p. So which forms new valence band as shown here, which provide the negative shift, upward shift of valence band maximum of the materials. So singular tendency can be found for iodide. This is chloride, I guess, and this is iodide. So from the result, if we can introduce bismuth to this site, we can change the orbital interaction around the bismuth, and we can tune the band gap of the materials. So this is, next topic is lone pair interactions. As I said, if the coordination environment is like this, the band gap is narrowed. But in this case, the valence band should be like upward shift, and the conduction band should be downward, shifted downward. But in experiment, valence band shifted upward, but we don't see the shift of the conduction band. So this is because we also need to consider the lone pair interaction in materials. So far we focus on intra-layer interaction, which means that we only consider the interaction between bismuth and oxygens. But in this materials, we have also another bismuth across the halide layer. So we also need to consider the interaction between this bismuth and this bismuth. So if we have 2 bismuths across the halide layer, these bismuths can interact with each other to form bonding and anti-bonding orbital again. And in this material, this bonding interaction between 2 bismuth 6p across the halide layer is contributing the valence band maximum, a conduction band minimum. This is the reason why when we change the halide from chloride to iodide, the conduction band is shifted upward. This material has highly disparate conduction band structure here, and this is derived from the bismuth 6p and the bismuth 6p interaction as shown here. But if we replace this chloride with iodide, this interaction between two bismuths is reduced because iodide has a larger ionic radius. So in this materials, the electronic structure of this material is like this. In valence band, the interaction between bismuth 6s and oxygen 2p mainly contribute to the valence band. On the other hand, for conduction, bismuth 6p and bismuth 6p interaction across the halide layer may contribute to the conduction band. So if we replace this halide layer from chloride to iodide, the interaction of this bismuth 6p is reduced, which narrow the conduction band with conduction band dispersions, and this is the CBM, this is the CBM. So if the conduction band is narrowed, the CBM is negatively shifted. So this is the reason why when we introduce the iodide to these materials, the conduction band is shifted upward. This is further supported by these 2 materials. the bismuth oxide selenide and the bismuth oxide NaCN. So if we change this selenide to this NaCN, the interaction of these two bismuths can be reduced significantly. So in these materials, the conduction band is derived from these two bismuth 6p orbital interactions, and so it's supported with CHP. And this material has dispersed conduction band structures which has the small effective mass as shown here. But if we replace this selenide with this large NaCN, the interaction between bismuth and bismuth is significantly reduced, which resulted in the less dispersed conduction band and larger effective mass as here. So in these materials, the bismuth-bismuth interaction is key to control the electronic structure of these materials. So from this result, we can say even though this layer doesn't contribute to the conduction band directly, but it indirectly contributes to the valence band because it determines the interaction between these two bismuth-bismuth orbitals. So next I'm going to talk about the effect of temperature on lone pairs. So far I described the static orbital B of materials of lone pairs. But recently the dynamics and temperature effect of lone pair is very kind of one of hot topics. For example, in this case, in germanium telluride, even in high temperature cubic phase, we have locally distorted environment in the materials. And another case is this materials. In this case, the dynamics of lone pair is reported to help the fluoride ion conductor. Another case is bismuth vanadate. Also in this case, we have distortion, local distortion in materials. And even in the perovskite structure, for example, in T2+ is laterally around the crystal structure, which can affect the optical property of the materials. So recent advancement of the PDF measurement, like X-ray and neutron measurement and MD simulation, allow us to analyze the lone pair dynamics. So I'm also interested in lone pair dynamics, and I'm going to show some more details of my recent work. So, for example, I'm interested in germanium telluride and tin telluride, and in these materials, lone pair is reported the key to explain the phase transitions. At low temperature, they have rhombohedral crystal structure where the germanium has lone pairs. In these structures, germanium is shifted from the mass center of telluride a little bit. So this is because of lone pair. In this case, lone pair is active. But at high temperature, this phase is changed to the FM3/M, which is the cubic and log salt structures. In this case, germanium is exactly at the center of telluride. In this case, lone pair is inactive. So in this phase transition, activation of lone pair triggers the phase transitions. So however, the detailed mechanism remains unclear. So I'm going to tackle this using machine learning force field. So the interesting point in this phase transition is the difference in germanium telluride and tin telluride. And they have the same phase transition pattern from R3M and FM3/M, but the type of phase transition is reported different. The phase transition temperature for germanium telluride is 700 Kelvin, and which is reported first order phase transitions. But for tin telluride, the temperature is 100 Kelvin and reported second order phase transitions. They have exactly same phase transition pattern in terms of the phase groups, but they have different pattern of phase transition from the order. So my hypothesis is that this difference is derived from the lone pairs. In germanium telluride, at at low temperatures, they have double wears. This means this is the center, mass center of the coordinated telluride, and this is a lone pair active germanium. So at low temperature, the lone pair is active. Lone pair on germanium is active, as shown here. And the key is the depth of this double wear. At high, by increasing the temperature with thermal expansion, this double wear the depth of this double wear is reduced, which enables the dynamical hopping of lone pair, as shown here. So in germanium telluride case, the lone pair is dynamically active, but from the average structure, which is on the center of these two double wears. But on the other hand, for tin telluride, this double wear at low temperature is very low. So with increasing temperature, this double wear is eliminated like this. And in this case, lone pair can be dynamically inactive. So this is the second order phase transition, and this can be faster the phase transitions. So to investigate this kind of type of phase transition, I checked the depth of double wear using TFT. So this shows the distortion amplitude versus relative energy. When this distortion amplitude is 0, which means that the materials has like cubic phase, where the germanium is at the center of the mass center of the telluride, as shown here. But when I move this germanium to 111 direction to here, which is on the header, the energy is stabilized, as shown here, because of the lone pair. So at the 0 Kelvin, the germanium is preferred to be distorted, as shown here, because of lone pairs. The 14 telluride, we have similar patterns, but the depth of this stabilization is different. For germanium telluride, we have like 150 MeV per form year stabilization, but for tin telluride, we only have like 15 MeV per form year stabilization, as shown here. So from this result, we can see the depth of double wear is quite different from with each other. So using this, I also tried the MRFF using BASP. This is just started from like 3 months ago, so I'm very new to the MRFF. But by using BASP, we can simulate the phase transition. As shown here, the phase transition occurs at 600 Kelvin for germanium telluride, which is the similar region to the experiment. And for tin telluride, we have like 100 phase transition around 100 Kelvin, which is also similar region as also observed experimentally. So I'm gonna go. So further analysis is ongoing. So up to now, I just simulated the phase transition with the materials. So another example of the effect of temperature of lone pair is on these materials. This material is Ba3O4 chloride, has isobar A structure at low temperature, but at high temperature, this phase has a tetragonal high symmetry structures, as shown here. So this is already reported from this result. However, what happened during this phase transition is not revealed. So I also trying to find the mechanism of this phase transition using machine learning force field. So one possible mechanism is here. At low temperature, we have double wear, but at high temperature, the double wear just shape of the potential energy surface is changing from here to here. So in this case, lone pair is active, but in this case, lone pair is inactive. This phase transition pattern is the same in the tin telluride case. But another case is like in germanium telluride, we can have active lone pair, as shown here. In this case, lone pair is locally active, but from the average structure, lone pair is inactive. So first I did some experiment on the synchrotron X-ray diffractions. So I visited spring 8 to determine the phase transition of these materials. And this is the synchrotron, and this is the world's largest third generation synchrotron radiation factory. So this is the result. So I'm not going to go to the details, but this shows the XRD pattern, and this is the theta, this is the temperature. By increasing the temperature, we observed the phase transition around 500 Kelvin, and this two peak merged to one peak, which shows that at low temperature, the phase has I2/A space group, but which is changed to the PU4/mm at around 500 kelvins. So phase transition from this phase to this phase is observed by using the in situ XRD measurement. So this is also simulated by machine learning force field MD. So we see that the phase transition around 500 Kelvin, so which is similar to experimental result. So I further analyzed the activity of lone pairs. In these materials at 100 Kelvin, the lone pair is active. This shows the shift of the jamming from the mass center of the telluride. This is the center of this is the mass center of the coordinated telluride. So about at 100 Kelvin, jamming telluride had lone pairs. But after phase transition, jamming telluride jamming doesn't have lone pair action here. At 900 Kelvin, jamming also doesn't have lone pair. So from this result, we can say at low temperature we have a static active lone pair, but I think at high temperature, lone pair is going to inactive, as shown here. So this is from this result we can say this phase transition from this to this is kind of second order like phase transitions. So although further experimental support like PDF analysis is needed, we think this phase transition from this to this is second order like phase transitions. So in summary, I talked about the static view of lone pairs. First one is inter-layer interaction. So lone pair is derived from the interaction between the post-transition cations and coordinated anions, as here. And also we also need to consider the interaction between two cation orbitals in these layered materials. And I also trying to understand the dynamics of lone pairs, which is my future work. So, but anyway, I think the understanding of lone pair is a key to design the materials in the future. Thank you.
Thank you for the very nice talk. I do have a question to start with, actually. And since you mentioned you use MLFF to calculate some of the dynamic behavior of your systems, what would be the reason for you to choose MLFF instead of like ab initio MD? Does it make a big difference? Because in MLFF you do have errors. Even you have the same level of theory, for example, R2 scan, you add some error to the prediction. So what would be the reason for you to use that?
Well, you mean because MD is very too expensive?
And maybe like in a smaller system, so does it?
I even haven't tried.
Okay. And the floor is open for questions.
Well, I'm interested in the operation of lone pair for DI peptide. You put DI into the high-temperature code where you cannot activate its lone pair.
Sorry? Sorry?
So you put bismuth atom at the
Yeah.
extreme side, which is high-temperature side. So you suppress the activity of the lone pair.
Yeah.
So in simulation, yes, we can fix it into the high-temperature code, so we can make it symmetric. But in theory,
frustration. Yeah, that is a very good question. And yes, I think one gap can be frustrated with related on pairs, but I don't know how can we detect that kind of like one gap frustration from experimenter side. Yeah.
Do you have other questions for Kenta? If no, let's thank Kenta again, and this is the end of the session. I believe we have a short break before the next session. Whatever. So you haven't really any idea at all, like before you try to what was the sales size? Was it on the left?
I don't know if I have a needle sizer.
will be Yang Hongzhang. He's a very good colleague, and he's good at research and knows a lot of insights into the modern part. So today he will talk about his recent work, which is published in Science, from CFT to AI, interface engineering in halide perovskite heterojunctions. Let's welcome.
You don't have to. So, yeah. Can you hear me well? Because I have a mic on my jacket, so I don't need to. So, yeah, good morning, everyone. Thanks for coming to hear my talk, and I'd like to thank Professor Seung-jae Shin for preparing this nice symposium and nice catering outside. So today I'm going to talk about my recent research that mainly I was performed when I was in Cambridge, and then I'd like to link my previous research with my current one, which I want to utilize AI for interface studies for halide perovskites. So yeah, the title is From DFT to AI, Interface Engineering in Halide Perovskite Heterojunctions. So before we go into the scientific part, I would like to introduce myself briefly. I obtained my bachelor's and PhD degree at Yonsei University, Korea in Seoul. And during my PhD, I was supervised by Professor Aaron Walsh, and mainly I was performing DFT simulations for metal halide systems to understand their uses, how we can use it for energy applications well. And then I moved to Cambridge to start my microwave fellowship position. There, I closely worked with experimentalists. So I kept discussing with my colleagues there using my modeling result and using their experimental observation result. We keep discussing, and we wanted to develop really unified research idea, scientific findings. And then now I joined UNIST as an InnoCORE fellow, and I want to combine the AI techniques with my modeling techniques to find something more interesting. So for those who are not that familiar with what is DFT, I just want to briefly introduce. So DFT is basically all about solving Schrödinger's equation using simplified formalism. So this is the well-known H-psi, E-psi Schrödinger equations. We may have heard of it during our quantum mechanics class or the university physics class, at least at once. By solving this Schrödinger equation in its full form, it is really hard and computationally prohibitive. Thanks to the great physicists and chemists, we got nice approximations and theorems to simplify these Schrödinger equations. In the end, we can solve it by only considering just the electron density rather than wave function. So we can reduce the dimension of the variable we are dealing with. And then as a result, we can solve Schrödinger equations using DFT in a simplified way. So in short, in many-body Schrödinger equations, we need to consider every interactions between electrons, ions within the system that we are interested in. But rather, we can take it into account as just electron density, and we only care the interaction between electron density in the space and ion. So to perform DFT calculation in practice, all we need is actually the structure of the material or system that we are interested in, because all the codings, algorithms are already there thanks to many programmers and computational scientists who developed nice package for us to solve Schrödinger equation using DFT. So main two output from DFT is energy and psi. From that, we can get the total energy of the system that we gave into the simulation package. And then as a result, we also get the electronic structures, the distribution of electrons around the ions in the certain geometry that we are interested in. From total energies, we can get some thermodynamic properties. From electronic structures, we can get some electronic properties. I'm going to explain some of these properties that we can obtain during my next slides. So halide perovskite has been used for PV and LED systems due to its unique properties. These days, when the researchers in this field are really interested in their 2D and 3D heterojunctions, because by making this 2D, 3D heterojunction using halide perovskite, people found that we can make more stable and more efficient devices. But still, we really don't know how their interface looks like, how atoms are arranged at the interface, and it results in how different electronic behaviors. So there was only one paper that actually tried to map how their interface would look like. In this case, they used the cesium-lead bromide and PEA-lead bromide as 3D perovskite and 2D perovskite. They observed epitaxial interface between two materials, as you just, not sure. Sorry, I didn't know it's not. Then let me use. Yeah, so here you can see the 3D perovskite, which is cesium-lead bromide here. Here you can see the 2D perovskite, which is PA2 PBBr4. And from there, by analyzing their intensity profile from their stem, they could analyze how the lattice spacing between each image would be. And then as a main figure, they measure the interlayer spacing or interface spacing, which is the distance between 3D perovskite and 2D perovskite. They observed it would be the 1.8 nanometer, which is 18 angstrom in angstrom case. But when I saw their figure, I felt something is off, because from the basic knowledge as a material scientist, the pristine surface termination of cesium-lead bromide, there should be cesium on top of their surface, not PEA. But people really haven't mentioned about how their interface would like, what kinds of cations would distributed at the interface. So I just decided to model the system, 2D, 3D heterojunction system, where there is a cesium on top of the 3D perovskite, and also at the same time I modeled the same system that was reported before, where PEA spacer molecule are occupying the top of the surface of 3D perovskite. So my main research question was how local configuration of atoms at the junction affects the property of the entire systems. And thanks to my colleagues and thanks to my group, it was accepted for publication in Science, so it will be officially published in next week. So please check out once it gets published officially. So here, this is the model that I used. As I told you in previous slide, we need atomic structures to run DFT, which is quite a large model. Although it is simplified version of 2D 3D heterojunction, it contains more than 400 atoms in each unit cell. I had to run simulation on that. So one thing we can get structurally, one value we can get structurally from this unit cell is actually the interface or interlayer spacing between 2D and 3D perovskite. So here I obtained the value of 17.6 angstrom, which well matches it with the previously observed interface. And then from the another model that has a cesium on top of 3D perovskite surface, I could get the much smaller value, which is about 12.8 angstrom. So 5 angstrom shorter, we can have 5 angstrom shorter interlayer spacing if we have a cesium on top of the 3D perovskite. So when we are calculating some interface properties, so we could easily see that this interface is a combination of the single 2D perovskite and the single 3D perovskite, and there's only difference is whether they have their counterpart materials in the unit cell or not. Which means if we calculate certain properties from this full interface cell, and if we subtract certain properties that we can get the 2D and 3D components, we would get some interface-related properties that arise from the formation of interface at this interface region. So first thing I calculated was the interfacial binding energy, as we can calculate total energy of those 3 different unit cells. by subtracting energies, we could calculate how strongly bind the atoms at the junction. And this is the value for the calculated interfacial binding energy. For case of cesium PA interface, we could get 20% higher or larger interfacial binding energy compared to PA-PA interface case. To understand why this one has a much stronger binding, we plotted charge density difference. Here we calculated the electron density, and we subtract the densities by using this formula there. And then here you can see the red and blue clouds. So red clouds means where electrons accumulate when interface is formed, and blue is where actually electrons came from. So alternating red and blue clouds around the interface means there is a interfacial bonding is actually formed at the interface, because they are the redistribution of the electrons upon the bond formation at the junction. But on the other hand, in case of PA case, we could see very, very small clouds because there are only interaction between hydrogens and benzene rings outer spacer part. But compared to this, in cesium terminated case, cesium and iodine also involved in interfacial bonding. So having different bonding nature results in different interfacial binding energy. And in experiment, we could expect this configuration would be more stable compared to the other one because it is hard to break the bond at the junction. And then more importantly, we are interested in when we make an interface between two different semiconductors, we always interested in their band alignment. So we plotted band alignment by analyzing density of states of this unit 2 interface geometry. In case of cesium PA interface, we could see that here yellow is the density of states for 3D perovskite. The green region is the density of states for 2D perovskite. So you can see that the VBM of 3D perovskite is higher than that of 2D, and then CBM of 2D perovskite is lower than that of 3D. So as a result, we could expect this type 2 heterojunction, where electrons want to separate if we get the photoexcited carriers. So electrons always want to go to the lower energy. So electrons will be accumulated in 2D, and then hole will be accumulated in the 3D if they have an interface with such interface geometry. In case of the PA interface, we could see that the CBM and VBM of 3D are both higher and lower than that of those of 2D. So as a result, we could expect type 1 band alignment, where if we have a charge excited carriers, they will all accumulate in 3D rather than separate into two different parts. That is what I predicted, what we predicted using DFT. And then we to further provide how the electron wave function would look like, I plotted just HOCO or LUCO of the unit cell. Here we can see separation of the hole and electron across the junction. Here we can see both hole and electron would be localized in the same materials, again, by plotting wave functions. We wanted to confirm the result from theory, because if there is a theoretical result without experimental validation, people hardly believe. And I don't have an ability to perform my own experiment like Kanta, previous presenter. I relied on my excellent colleagues in the group. So this experiment was performed by my colleague, Dr. Yang Lu. Actually, to make that junction, we designed the experiment where normally in the field of halide perovskite, or even people who make a 2D, 3D heterojunction, people always relied on solution-based process where they want to spin coat certain material on top of something. But in that case, we cannot hardly control the local atomic geometry at the interface. Rather, we use the 2D single crystal as our substrate, and we try to evaporate the precursor for 3D perovskite, and then we grow the 3D film on top of 2D single crystal substrate. So here, as a result, we could see very nice epitaxial behavior of the growth. As you can see here, you can see the align of the certain C star vector axis, which means they have a preferred orientation along C star direction, and then we can see the plane, the lattice vectors, the points are really perfectly aligned in the XRD patterns. And then we measured from our growth sample where there is the session PA interface. Firstly, we measured the HADAP stem. We could see the image, and by analyzing its intensity profile, we could get certain value, which is 2.5, which corresponds to the interface distance. Thankfully, it matched well with my previous prediction that resulted in DFT. And then we also tried to make an interface where there is a PA on top of 3D. To make this geometry, we applied one trick. So if we just directly grow 3D perovskite using this precursor on top of 2D, we always get this type of interface heterojunction. But to insert additional PA spacer on top of 3D, we actually evaporated PA bromide precursors in advance for a very short time so that we can distribute PA spacers on top of 2D, and then we try to grow 3D perovskite later. And then as a result of that, we could see this PA-PA interface, which is well-defined interface. And then from the same intensity profile, we could get the value, which is about 17.1 angstrom. So we could see it around 5.5 angstrom difference in their atomic geometry, which well corresponds to our DFT simulations. And we further wanted to confirm then band alignment, the theoretically predicted band alignment can be really realized. There could be a lot of ways to confirm it. Not a lot of, there could be several ways, but we try to measure the time-reserved PL spectra to track how carrier behaves at the junction. Here you can see in blue curve, which is for PA-PA interface, from red curve, which is the CS-PA interface. At the very initial moment, after like 10 nanoseconds, first thing we could see is the decrease in PL from CS-PA interface is much faster than the other case, like a PA-PA interface, and this is the control sample where we only grow the 3D on top of glass. But after 1 microsecond and up to 10 microseconds, we could see that there's a long-standing the tail of this PL peak where there's no long-standing PL tail for the 3D control sample and PA sample, which means charge really separates at the junction. So we have a separated hole and electrons in both sides, so they need a time to actually recombine and emit a photon in their geometry. So as a result, we can get really longer tail. Same thing happens for 2D. So when we excited the sample with a laser that has a larger band gap for both of the materials, which is 400 nanometer, and then here we tracked the PL from 3D and PL from 2D. For both of materials, we could see long tail, which means the charge separation. And also when we integrated this PL intensity, what we could confirm was that for after 1 microsecond, in case of PA-PA interface, more than 98% of excited charge carriers are recombined, and only 2% of them emit after 1 microsecond. But in case of CS-PA interface, only more than 70%, less than 70% are recombined before 1 microsecond, and then there are more than 13% that recombines after the 1 microsecond, which is same result for the longer tail we observed there. So we observed that phenomena, and we understand then what really determines the band alignment between two materials, like here, 2D and 3D perovskites. So when we are talking about band alignment at the junction for two different semiconductors, normally there are two main contributions. One is the natural band alignment, but the other one is built-in potential. So natural random alignment, it is mainly from the different surface termination of the material that we have. Depending on surface termination and orientation, we have a different absolute electron level, and it affects the band alignment of two different materials at the junction. And also, once there is a interface is formed, there is an interfacial bond happening, and then as a result of that bonding, we could see some built-in potential because they are donating and accepting electrons at the junction. It makes the potential difference. So we analyzed then which one is the dominating factor when we are determining the band alignment between 2D and 3D perovskite. Here, firstly, I plotted the natural band alignment where these values are the case where they didn't form interface when there is a 3D perovskite and 2D perovskite alone, but maintaining the same lattice orientation and termination that I showed in previous interface geometry. So I plotted the electrostatic potential and aligned two different electrostatic potential by using macroscopic average. And then what I could see is that when we match their macroscopic average of electrostatic potential as a 0, and then we could see there is some difference in their vacuum level, which is about 0.5 volt, 55 volt here we could see. And then same number of the shift in absolute electron level was observed, like 0.55 you can observe here. So if we have a PEA instead of cesium, it results in the larger the dipole due to its geometry, molecular dipole, and it raises the vacuum level by 0.5 volt, and it affects to their neutral band alignment. And then I also analyzed then how much the built-in potential would be when they form an interface. This is again, charge density difference that I showed you in previous slide. And then by quantitatively analyzing, by integrating along this direction, we could see this intensity profile along that direction. And by solving Poisson's equation for that charge density difference, we could get potential difference across the junction. As a result, we could get the built-in potential is around just 0.03 volt, which is one of order lower than natural band alignment. So yeah, this result we confirmed that. So in 2D, 3D perovskite, unlike conventional the semiconductor heterojunction, the surface termination or having the spacer on top of certain material really affected their band alignment, rather than the built-in potential due to although their bonding strength is relatively small compared to conventional semiconductor heterojunction systems. So it only results in very small shift. So their band alignments are predetermined by their natural band alignment, and there is very small role of the interface formation. We further wanted to utilize this finding. We know that now spacer is really important to control their natural band alignment. So, and thanks to its large chemical library for halide perovskite, we can choose a lot of different A-site spacers that can replace PEA. So, and then among those many candidates, as a theorist, I was typically interested in the fluorination of this benzene ring because I already have a model for the previous system. All I need to is just substitute one hydrogen with fluorine and then perform the same calculation at much lower cost, and then I can see the trend. And then I can discover some hidden design rule to make a better heterojunction for LED or TV device. So I decided to gradually fluorinate one of the hydrogen at the benzene ring. So here, this is one of the hydrogen at hydrogen 4 site was substituted by fluorine here. I can just two of them, so 2,6 FPA, 3, 4, 5, and then theoretically we can substitute all of the hydrogen into fluorine. And then as a result, we could expect the dipole across the spacer, and I we thought it can affect the actual band alignment of the system. So here, how bulk parameters changes over fluorination. So there's no huge difference in terms of their band gap because they hardly contribute to their valence band and conjunction band minimum for halide perovskite systems. Rather, they only make a little distortion to octahedral cages in the system. So first, I again calculated how binding energy changes upon the gradual fluorination. So once I have one 4F-PF, we could see slightly stronger interfacial bonding compared to the PA case. And 2,6, it has a slightly decreased, but there's not so huge difference. But in case of 345 and 2,3,4,5,6F case, we could see the very drastic decrease in their interface binding energy. It means having a lot of fluorine at the junction may be not good for strong bonding. So, and then by calculating their charge density difference for the 345 and 2,3,4,5,6F PA, we could see change in their shape. So in case of PA, 4F PA, 2,6 PA, we could see strong charge accumulation region at the junction. But instead, if we have too many F at the junction, then it forms the charge depletion region. And as a result of a different bonding profile, we could see decreased bond strength. And then more importantly, by plotting this DOS, we can summarize how fluorination really affects their band alignment, which is somewhat quite extreme in case of like 345. So their offset is more than 1 eV just by having a lot of fluorine at the outer spacer. In case of 2,6, they form, because this is the case where one side is terminated with CS, and the other side is terminated with spacer. So only 2,6F PEA case, they form type 1 heterojunction, whether the other one has a type 2. Maybe it is due to the different dipole orientation, because having many fluorine in the inner ring of the benzene, maybe it doesn't create enough dipoles that can shift their band alignment. So maybe that's why we could observe type 1 band alignment only for this, the spacer geometry, and then we could expect the other. So unfortunately, we don't have any experimental support for this work because we just published the one work, and then this is what the expansion of the previous work as a theorist. But we are in close keep collaboration. So maybe in the end we can get some experimental support that can explain this shift from experimental side. But at the moment, this is on theoretical result only yet. So before I go into the next part of my presentation, I'd like to thank my research group and Dr. Yang Lu, who mainly performed the experiment for this work. And then just short take-home message for my first part of talk is, by fine-tuning local interfacial geometry, we can control the behavior of charge carriers in entire heterojunctions. And now, since I joined UNIST as InnoCORE fellow, I became interested in the use of halide perovskites in hydrogen catalyst systems. There have been several reports that use halide perovskites to solar to hydrogen conversion and hydrogen production or H2 evolution. Interestingly, this case, they only used halide perovskite as a charge carrier generator. They are used just to absorb light and then just provide electron and holes to the other co-catalyst. But interestingly, in this paper, they used just halide perovskite as it is, as a catalyst, and they could see some the catalytic activity. To model such heterojunction system, unlike the previous solid-solid interface, we need to take care of their waters, which is interfaced with solid. And due to the dynamic nature of this liquid, we no longer rely on DFT because DFT doesn't have a temperature. We only see static image. But for catalytic systems and for liquid-solid interface, the dynamic nature of the liquid is really key to understand their catalytic behavior. So it's been only 2 months since I joined UNIST, so there's not so many results for my research direction. But I want to address this problem. I wanted to rely on the machine-learned force field approach. I heard the next presenter, will give us a really basic of this approach. So by using this machine learning-based approach, we can accelerate the molecular dynamics simulation that can actually see the dynamics of the perovskite and water molecules. And then still it is really naive image. I should make some changes in this model to precisely track how the proton is really generated on top of the surface of halide perovskite and so on. So as it is, we have many AI, MLFF experts here. I want to openly discuss. For my research direction, I want to accept any of the advice or comments during the Q&A sessions and any questions too. So yeah, this is all I prepared for today. And there's a lag just. There's nothing, yeah. So I'd like to thank you for your attention. Yep. Yeah, it is halide perovskite. So there are so many combinations of halide perovskite. Thankfully, cesium lead bromide, the people used for their demonstration here, yeah, they are somewhat stable compared to the other composition of halide perovskite. Pardon? Yes, without any co-catalysis. In some cases, people add some platinum on it to make it the more efficient. But yeah, interestingly, this was just reported this year. They mentioned without using co-catalyst, they could see. And they got, so one key message for this one is, they used just cesium lead bromide as a single catalyst for hydrogen evolution. And then they tried to alloy potassium into cesium. And then they got like 11-fold increase in terms of catalytic reactivity. Still, they are mentioning that it is due to the change in their absolute electron level, having potassium near the surface that can alter the electron levels, and maybe it can be beneficial for the accelerating hydrogen evolution. It is their assumption, their hypothesis, but I want to confirm that too, if I can give a cesium on top of the surface, whether it really boosts such catalytic reaction or not. And then, what is your second question? Yeah.
How we change the alignment by changing the switch across? And in my sense, the key for this one is the softness of if we change the outright, it's bromide chloride.
Yeah.
So in my sense, the alignment will be more increased.
Yeah, having different halide definitely affects from 3D side, but if we have a different, let's say, so here we only used bromide system. The one advantage of having same halide here is we don't see any the halide separation across the sample, because we all know that halide perovskite are really nice ion conductor, and then only when they have the same type of halide, they can match their lattice. If we have one side like iodine, then they are no more epitexture. then due to their lattice match, maybe this figure will not no more valid. But if we just change entire bromide system into entire iodide system, it could behave in the similar way, but since they have a much smaller band gaps, so maybe the role of the dipole moment of spacer plays the much higher role, I think. But yes, we can tune from 3D side, but only when they can make this the epitaxial interface, I think.
No, I have one
Yeah.
question about the 3D and 2D interface.
Yeah.
So if you share screen for them, like will they grow?
Yeah, maybe. I don't have any idea whether they would slide if we give. But yeah, when I make a model, I also tested different binding site because they can have a AA stacking or AB stacking. So they have a certain preferred stacking sequence. There is some energy difference for that. So maybe there be a chance be the slide into certain part, but thermodynamically there is a certain the favorable binding site at least. Yeah.
So if your question, let's start with the speaker again.
Thank you. Yeah, this is the mic, and I guess. Yeah.
Thank you for the exaggerating introduction. I'm far from an expert since I just basically finished several projects on MLFF, so I'm still learning at the very beginning stage. But so for my talk today, it's going to be slightly less advanced comparing to Yang Kwang's, and I'll focus a little bit more on the basics of my theories and methods that I use in my study. Okay, and to start with, I'd like to introduce the background of my study. So I finished my MEng project, which is actually a combination of undergrad and master projects at Imperial College, Materials Department, and also had my PhD done in the same place. And on the right-hand side, you can see two pictures we took from our PhD group. You can actually see more than half of the speakers presenting today, so we all connected in one way or the other because almost everyone has joined Aaron's group for a PhD or a postdoc. It is quite slow for no reason, but is it controlled by the laser? So for my project, what I'm doing actually, so I'm focusing a bit more on the electronic side instead of, more on the structural side instead of electronic calculations like most of my colleagues have presented. So for this one, actually, I focus more on halide perovskite, again, the one Yang Kwang presented, but more on phase transitions and dynamic disorders of these systems. So for that, I'll have to use molecular dynamics. But instead of using ab initio molecular dynamics, which can be slow and limited in sizes, I use machine learning-based molecular dynamics. And once I have these MD trajectories, I develop methods that analyze these trajectories and output useful quantities that can describe the structural behaviors. So for that I use MLFF. So here I'll give a very basic introduction on what these algorithms are. So basically you input a structure to these algorithms and it gives you the energy, forces and stresses through a complex set of parameters and linear equations basically. So in MLFFs you can actually achieve this through several means. But in the basic and in most conventional ways, like classical force fields, you use very simple functional forms using simple equations like for this one, Lennard-Jones-Buckingham potential. You only need several parameters for every element, which is very fast, but then you also lack certain accuracies. And in the middle, you have this DFT, which Yang-Kwon just explained. You have these first principle methods, like this one here is the Kohn-Sham equation used to compute quantities from DFT, which is very slow in terms of your system. You can only limit it to maybe hundreds of atoms would be the maximum for ab initio MD. And ultimately we get to these machine learning models that only emerges maybe 1 or 2 decades ago and only past few years for integrating into force fields, is that you have these complex set of neurons in layered manner that can actually take in high-dimensional information, for example, structural information, and output energy, forces, and stresses. You can train them properly. And for each and every force field, there are 2 main components. The first step is, of course, the description. You convert the structure into a set of descriptive vectors that can actually be understood by the machine. And then the second part is the regressor, which you learn from these descriptive vectors to your output energy, forces, and stresses. For this descriptor, one key assumption is actually, it assumes all atomic energy, forces, and stresses is exactly described by its local environment, which is, we know, it's not definitely true, because there must be long-range interaction to some sort. But in these algorithms, we simply assume this to be true to speed up the calculation. So here is one of the algorithms that have been commonly used, which is the Gaussian approximation potential. I remember some of my colleagues have already used this, including Kanta in his study. And this one is actually quite simple. You use SOAP, which is smooth overlap of atomic positions, sorry, to describe local environment, which is basically including only the 2-body and 3-body interaction, so a really simple formalism, and convert the local structure using these density distribution function and into a set of descriptor vectors. And then you use kernel functions, which is basically comparing your input structure here with a set of reference structures and output the similarity as a kernel function, and basically just do the linear combination of all kernels together to output the quantities you want, like energy, forces, and stresses. So this is simple because it is only an overlap of functions, but also it adds complexity if you have more reference structure, because you need to compare more and more structures. So this is actually not really favorable if you have very complex environments. However, for this particular force field, an interesting function they added is the on-the-fly learning of structure. So basically, the core idea is that you can do DFT calculations whenever the force field is not strong enough, but once you have learned thoroughly through the local environment, you can actually go into the machine learning prediction stage that can speed up the calculation by a factor of probably 1,000 to 10,000, which is favorable for strong acceleration. And also, on the way of this MD calculation at the very beginning, the force field is weak. You need to do loads of DFT calculations. But then later on, you have machine learning prediction kicking in that can speed up the calculation. And you can actually collect sets of DFT frames that can well represent your, your local environment. And you can also use it for training other force fields. And here is a new, not really new, but a formalism called atomic cluster expansion that can be used to describe local environment in a new way, which is basically not just looking at this complex formalism, but the core idea is that you can represent any body order interaction with a collection of two body interactions by just taking the product of the descriptor vectors, which is really smart, proposed by Ralph Strauss almost a decade ago. But then some people could easily use these to speed up the description stage in MLFF. One really famous algorithm is called MACE, or multi-ACE calculation. So they do this by using only the pairwise interactions and go through the atomic cluster expansion formalism and then feed everything into message passing neural network, which is well known for strong description of local environment depending on connectivity. And with this combination, we can actually achieve both fast computation and high accuracy prediction of energy, force, and stresses, which is exactly desired for a strong MLFF algorithm. And so here I'll go into after explaining the basics, I can go into the very first project of my PhD study, which is how to actually use these large-scale MD to run useful calculations and get useful structural information from them. So here is one of the code that I developed to do this, which is when you feed in the MD trajectories, like these very large structures, maybe containing more than tens of thousands of atoms. But the basic building blocks of these perovskite is still the octahedra, as shown in here. And they can actually deform in two ways. The first is octahedral tilting, which is rotation of it around the three axes. And also by space group, it can be uniquely defined that the distortion is categorized into 4 different symmetry conserving distortion modes. So ultimately, every single octahedra in the trajectory can be described as 7 numbers, basically. 3 tilt angles and 4 distortions. And also it outputs other useful descriptors like lattice parameters, molecular orientation, if the A site is a molecule, just like maybe the PA described by Yang Kwang. And also people use MA or FA molecules depending on the needs. So ultimately you have a set of descriptors and you can describe any perovskite structure in space and time. So this is a bit different from what people would usually do conventionally, because people use reciprocal space based methods like in X-ray diffraction, for example. But this particular real space method that I developed is more convenient and applicable to these large structures because they can be very expensive. If you have very large structure and you want to do reciprocal space calculations. And also gives you direct intuition on the structure because it can be easily understood, and also reviews origin of disorder easily as a complementary methods to the conventional ways. Okay, so to give a very simple example, this is what the structure analysis would output. So on the left is the dynamical distribution of tilt angles along 3 axes A, B, and C. And this line, outer line, is the histogram or distribution of tilt angles. The shade below is the first nearest neighbor correlation of these tilting. So you can see that for the first 2 axes, there's no tilt, no correlation, basically. And on the third axis, you have a non-zero tilting because you have 2 peaks. And also, almost all of them is positively correlated, which means that just like in this structure, they're all tilted along the C-axis as the vertical line, and they're all tilted along the same way. So this is what it tells. So this is directly corresponding to one of the most common phases, A0, A0, C+, in cesium system. So this is the I3 MBM space group. And also you can use it to describe dynamical change of these quantities. So this is the tilt angle change with temperature as you cooling down from cubic phase, so no tilts, and to the trigonal phase where you have separated lattice parameters. And this is the tilt angle distribution. Also you see this signal of non-zero tilt as you cool down. And for a more complex case, I can study the cesium-lead mixed halide system. So you can actually, for every single dots here is one calculation as shown in the last slide. And then according to tilt angles, you can easily quantify and unambiguously what's the phases of these temperature and chemical compositions, and put everything into a phase diagram as everyone would do from experiment. And this is matching almost exactly with what you got from experiment. There is a transition from cubic to tetragonal to orthorhombic phase, and the structure is just shown on the right-hand side. And going deeper into the structure, not just looking at everything as a bulk, we can also look at the dynamic disorder of where tilt domains actually form. Dynamically, they appear and disappear, and this is actually important in this experiment because people do X-ray diffraction on the structure at certain temperatures. They see not just Bragg peaks, but also diffuse scattering away from the Bragg peaks. And this is actually the origin, and I can model it from the atomistic level. So on the left-hand side, you can see this very simple model of how octahedra tilt in 3D space. So if this octahedra rotate around the z-axis, it also have to drive the tilting of its neighbors because they're rigidly connected. But this is not necessarily the case for those that is not in the same plane. So this definitely will lead to domain formation in the dynamic manner. Just like these. So you can actually see tilting forms domains in 3D space along all three directions. So we can see these actually being played in 3D space because they are they're correlated stronger in plane but not out of plane. So you can see this, most of them is like pancake or plate in 3D space. And these simulations is actually in a quite large supercell of cesium lead iodide. So that's 24 by 24 by 24 unit cells, which is like close to 70,000 atoms, which is modeled by ACE model. And then I can analyze it with my code and then output these tilt maps. And just statically looking at these tilt domains, you can see that with different A-side cations like Ma and Fa, they actually form different size tilt domains. And I can define the size of these tilt domain by taking the dimension of its in-plane dimension and divided by the out-of-plane dimension to define how this domain looks like, which is basically this. So you can take the length in the parallel direction and also the length in the normal direction and take the quotient. You can actually get this ratio of the shape. And these lines is what I calculated from my calculation from MD analysis. And these triangles are what I get from experimental measurements from X-ray diffuse scattering, which is actually done by my colleagues in Sam's group, Milush, which is also the colleague of Yang Kwang during his postdoc. And speaking of the force fields, how do we actually define how good the force fields are, which is basically the most conventional way is looking at the errors. So here I'm showing the MACE model I use, also train Allegro models, and also comparing to the VASP gap model that Kanta described in his project. And MACE outcompetes the other models in terms of energy and stresses. Sometimes Allegro performs better in stresses, but both of them are actually quite good in this system, training on exactly the same training set. But both of them you can actually achieve force error less than 5 MeV per angstrom, which is already really good. You couldn't even get better from just the DFT errors anyway. And some people would recommend using the foundation model, which is actually models trained from the whole periodic table. So, for example, the Materials Project database. But for this material, actually, it's not as good as what people expect. So the gray line is the predicted phase transitions on cesium and iodide using the foundation model, and the orange one is from my calculation. And from my calculation, it's only maybe 10 to 20K away from experiments, but for the MP0, it's actually more than 150K shifts to the downside from the real values. And also people would be interested in how vibrations are predicted by the force fields. And here is cesium lead iodide under different phases and what the phonon dispersion looks like predicted by DFT, as well as maze models and Allegro models. So you can see that both models are actually quite good in describing the vibrations of these systems under different phases, and also you can see that on the cubic and the trigonal phase you get negative contribution of the vibration frequency, which means that they are unstable. Of course, the only stable phase is actually the orthorhombic low temperature phase. And just to go a little bit further, I can look at even more complex and even larger systems with the analysis method, which is, again, going back to the three mixed systems, MA, cesium, and FA, lead, mixing halide perovskite. You can actually see how phase transition differs in different systems. So here is exactly the same graph here showing a heating run of the structures. You can actually see how tilting changes from high tilt and low symmetry phases to low tilt, high symmetry phases. And you can actually define exactly when this phase transition occur, because tilt go from non-zero values to zero values. So you can see two phase transition occurs, from one in here and one in here. And you can actually see what is the crystal orientation after phase transition, just like in here. So here is showing that for these, maybe this one and this one in the high temperature phase transition in cesium and FA systems, you can see the orientation of the ultimate grains are actually random, so there is no specific orientation to be crystallized after phase transition. But under certain phase transition pathways, for example, these limited or guided ones, you can actually see they form specific orientations because they're controlled by the space group relations. For example, for this one here, the low temperature phase transition of cesium system, they must be crystallized along certain paths, and that's exactly what you would expect from a second order phase transition. But also you can see a well-known first order phase transition of the low temperature phase transition of MA system. You couldn't actually crystallize a low temperature phase from the tetragonal phase, which is because of the molecular orientation restrictions, which is also predicted in experiments. Measured in experiments. And in this mixed halide system, we would also be interested in how the halide distribution would change the structural behavior. So here I'm showing three structures. So here is the random distribution of halides all the way to segregated halides. And I do this by a simple Monte Carlo simulation of halide swapping. So here showing, in short, it's quite a complex figure, but in short, this one is showing that you have heterogeneous tilting correlation in space, and also you have determined crystallization of orientation, also a lowering of phase transition temperature as you go through the halide segregation process. And in particular, I see this very interesting phenomenon where in random distribution of halides, you see exactly the same space group as you have from the purer counterparts. But if you have segregated halides due to this local strain, you cannot crystallize the same space group from what we generally understood from the purer halides, but also you have a different tilting pattern. So actually, here is the random one, everything is homogeneous and nice, but however, if you have segregated halides, you actually see these locally inhomogeneous tilting patterns, so completely different from the one in the pristine regime. And they are also strongly correlated to how bromine-rich regions and iodine-rich regions are distributed. So there are no tilts in these iodine regions, but strong tilts in the bromine-rich regions. And these are all interesting because they are actually captured in X-ray diffraction in experiments, which I'll show maybe a bit later. And this is an ongoing, or actually finished project to be submitted soon, which is with this new MACE MLIP interface that had just been released several months ago. They actually integrated a CUDA equivariance module into the MACE algorithm and can speed it up by a factor of almost 8 times, and also allows way more atoms to be modeled on the same GPU, so they managed to get a better memory control. So with this new algorithm, I can actually model the organic perovskite to 18 by 18 by 18 supercell. which is already close to 80,000 atoms around. So in this way, I can actually find a very interesting phenomenon, which is static long-range disorder in Fe-lead iodide systems. So at higher temperatures, you still have cubic phase. Middle temperatures, you still have the gamma phase. However, at even lower temperatures, I see the static domains being formed, just like what people would say as twinning at very low temperatures. This is mainly because of the molecular orientation, but I wouldn't detail here due to time. But these are actually, so I predicted this from my simulation, and I asked my colleagues Milush and Cambridge, and they actually found exactly the same phenomenon, which is quite surprising. And that is they use X-ray diffuse scattering, which is these plots, which is basically Q-space resolved X-ray diffraction. And here I'm showing on this very right panel at 50K, or the very low temperature. Here is my simulation, which is you actually see diffuse peaks away from the Bragg peaks as shown in here, and also having quite a good matching with the experimental measurements. So experiments, you also get nice Bragg peaks at middle temperature, but at low temperatures, which they didn't measure before, but I asked them to do this and actually find the same distribution of X-ray diffraction peaks. So these are mainly because of molecular order. So in this way, when I control the molecular order, I can actually get the nice gamma phase. But if I just do random molecular order and then do the same cooling process, you have strong diffraction coming from this static disorder. And just to mention a little bit about electronics, because my colleagues are doing electronics, and maybe this could be interesting as well. So these, no matter it's dynamic or static domains, these tilting always lead to change in local band gaps. So I do this by subdividing the greater structure into smaller cells and then do DFT calculations on them and fold the band structure back to the first brilliance on the low tilt region. Low band gap within the low tilt region, which is the dark background, and the high tilt region, which is the bright background. You have high band gaps, which is exactly corresponding with each other with strong correlation, and you can actually see even the structure is pristine with no modification or defects. Just the tilt domains could lead to fluctuations in band gap locally. So with that, probably I'll just conclude to make a very quick summary, which is combining MLFFs, you can actually achieve, you can get a powerful simulation tool for multi-scale modeling, and you can use one for data collection and one for production. And also large-scale MD reviews behaviors that are not captured in conventional ways, because obviously you couldn't have domain information in small cells. You can only see them in large cells. And that's probably all for me. And I'd like to thank my colleagues in the group, especially the collaborators from Cambridge for doing the experiments for me. And that's all for me today. Exactly. So I would assume that would be one of the future projects I have with Jay here, actually, I believe. But yes, I haven't looked at any structure other than pristine structures, because so far we've been focusing on just the pristine structures. But that's definitely, that can be easily transferable. The whole analysis framework could be easily transferable to any, neither it's 2D or 1D or interfacial perovskite structures. Yes, it would be easily transferable. Yes, exactly. Yes, that effect is taken into account. So you actually crop the larger supercells with respect to the spacing of the B sites. So it actually takes into account the contraction and expansion of the cell into the DFT calculation. So yes, it's taken into account. And that's also one of the factors. So you couldn't actually isolate the effect of tilting,
because that's effectively linked to local lattice parameters as well. So there's no direct link, but also it's like at least an implicit connection.
Thanks for your very nice introduction, Kanta, and I'm very happy to see all of you here and online as well. So today I'm going to talk about the perspective about computational electrochemistry in the era of AI. So I would like to briefly introduce today's talk. So it has three contents. The first one is introduction about the foundational theoretical framework for electrocatalyst modeling, and then I'll move to show you some recent electrocatalyst modeling, and finally I'd like to show you my group's development for treating the recent electrochemical interface modeling. So let's think about what the computational chemistry is. So it is basically the study of the physical chemistry to describe or explain the phenomena in electrocatalysis or electrochemical interface. So the baseline model for this one is known as computational hydrogen electrode model, which was mostly developed from Professor Noskov's group. And the basic idea for this one is to express the chemical potential of proton and electron, and it is very challenging to quantify or calculate chemical potential of proton or electron in computational matter separately. So the basic idea of this framework is to express this chemical potential at the same time with using the chemical potential of this gas molecule and experimentally measurable values like pH or electrode potential. Then we can describe the binding energy of certain process. Let's say we are curious about the mechanism of oxygen reduction reaction on the PT catalyst. Then we are eager to measure the binding energy of this adsorbate formation step. So we can then calculate the binding free energy of this adsorption step by measuring or quantifying each Gibbs free energy, like calculating PTOH step and calculating the free energy of this bare surface and gas molecules free energy and free energy of these proton and electrons. Then the merit of this approach is we are able to explain or investigate the reaction steps during the oxygen reduction reaction. So let's say we are interested in the chemical reaction mechanism for this oxygen reduction reaction step. And experimentally, it is well known that its standard reduction potential as 1.23 volt. Therefore, the Gibbs free energy change has to be 4.9 around eV based on this narrowing. We have some technical issues, so please bear with me. 아닌데요? 예. 계속 쓰던 건데. So this oxygen reduction reaction is well known that has four reaction mechanisms. The first one is the oxygen activation step by formating this PTOH intermediate. And then the next step is formating PTO adsorptive step by making one H2O molecule. And then the next step is known as formating PTOH step. And the final step is known as returning to the bare PT surface by making another H2O molecule. Then, based on the CHE framework, we are able to express or calculate the free energy change during this chemical reaction. And this is at the experimentally measurable electropotential at 0 volt. Then by controlling the chemical potential of electron, which means we control the experimentally measurable electron potential value. So here you can see that the potential is set as 1.23 volts. And let's say we control this chemical electrode potential value as between 0 volt and 1.23. Here it is set as 0.9 volt. Then you can see that based on this Gibbs free energy diagram with respect to this reaction coordinate, you can see that at 0 volt there's no thermodynamic energy barrier, but in 1.23 volt it has some free energy barriers here and here. It means that this is not spontaneously proceeded at this electrode potential condition. However, thinking about the experimentally measured standard reduction potential, it is supposed to be happen in the spontaneously occur at this reduction potential condition. So we need extra energy to make this chemical reaction spontaneous, which means we need extra voltage from 1.23 volt to 0.9 volt. So at this potential condition, you can see there's no thermodynamic barrier during this reaction. So in principle, we are able to calculate the theoretical overpotential value within this framework, which is 123 volt minus 0.9 volt. So we can estimate the overpotential value theoretically as this value. So another well-known phenomena in computational electrocatalysis is scaling relationship. So it means that those binding energies between different adsorbates are linearly correlated. So this is known as scaling relation. So we can then explain by using single adsorbates binding energy as using it as the descriptor for this reaction, and the seminar paper explained the different ORR activity by using this oxygen binding energy as using it as the descriptor. And then the last thing that I like to mention in this CHE framework is the dependent center theory. So let's think about why this metal species or metal catalyst has different activity, and it can be predicted here as it has different binding energy. Then let's think why this metal has different binding energy, and it is explained in this framework as dependent center theory. So the binding energy between this metal catalyst and adsorbate is determined by based on the position of d band of this metal catalyst. So the main idea of this theory is to explain by measuring the d band center, which means the averaged or some calculated Fermi energy position by plotting this binding energy as a function of this relative position of the d band center. We are able to explain the trend of the different binding affinity of different metals, and then we can explain the different activity of different metals on each chemical reaction, like oxygen reduction reaction. So let's recap this fundamental framework. So pros of this approach is really simple and very fast because it never consider any details of electrochemical interface. It only includes vacuum state, like single crystalline surface with a vacuum condition. But cons of this approach is it ignores many details, like it never considers some applied potential, but I show you that we seemingly it is able to control the different potential values, but it is not explicitly charging the electron. It just controls the chemical potential of electron by using the macroscopically measurable value. So in our theoretical community, we are eager to see more atomic scale or microscale phenomena by charging this interface. And we also neglect many details on the electrochemical interface. Let's say we are trying to understand the details of oxygen reduction reaction. No one knows details whether the interfisher water molecules or cations or anions is involved in this reaction or not. But this CHE framework is unable to discuss that details. So this is why many of the community members like to make this approach more advanced. So I'd like to show you some recent development for realistic electrocatalyst simulation. So on top of CHE model, many of theorists gathered together and like to discuss further development to make this modeling more applicable to experimental side. So basically the conclusion by far is technically very hard to do the electrochemical interface modeling or electrocatalyst modeling. The main reason is like this, and it is mostly out of the multi-scale nature of electrochemistry. So many of theorists just focus on the outcome or result of experimental measurement, which shows the relationship between the product, which shows shown it as the current density of the product, and with respect to or as a function of the electrode potential, which is the main driving force for this reaction. However, experimental setup is way more complicated than we expected. So it consists of, let's say we are curious about the CO2 reduction reaction, then the experimental setup must be like this, and it also includes some many of electrolyte component and reactant, and it also includes some very complicated membrane or some porous electrode and very complicated shape of this configuration of this cell setup. But in theoretical side, and theoretical people always just consider about this one, not focusing on this multi-scale nature of electrochemistry. So this is main bottleneck to fully understand the electrochemical interface or electrocatalyst for theorists from the experimental measurement results. So common approach that many of theoretical community members use is to decouple or to break down whole system into each regime that they are able to explain. So let's say we are curious about a kind of macroscopic transport phenomena during the electrochemical system, and it is the most basic electrochemistry, like Butler formal theory stands on. So for dealing with this phenomena, we have to set the Goban equation as transport phenomena equations like Navier-Stokes equations or Fick's law like this. And if we are interested in kind of microkinetic rhythm, mesoscale, if we are interested in how the different observates are formatted during the reaction, we have to focus on kind of micrometer to millimeter scale and kind of second scale phenomena. Then we are supposed to dealing with this kinetic region. So we have to rely on some microkinetic modeling or kinetic Monte Carlo simulation, which solves kind of mathematical expression to deal with this. So the last point that I'd like to mention is to understand this electrochemical interface, with the atomic scale resolution. So to deal with this more details between the electrode and electrolyte or reactant, we have to solve or we have to understand the electronic structure between the charged electrode and electrolyte or reactant. Then we have to rely on quantum mechanical simulations like DFT. So I'd like to mention many of details today around here, and it also includes molecular motion. So we often use molecular dynamic simulation as well to deal with this phenomena. So I'd like to mention some of challenges for this regime. And the first one is how to express operand electrode structure. So let's think about and imagine what the experimentalists think about. So based on this paper, many of experimentalists use porous electrode for making higher activity during their measurement. So this is also in CO2 reduction reaction electrode cell. So here you can see that CO2 is reduced to high valued product, and here this electrode is mostly from the kappa, and you can, even though we characterize this kappa electrode as 1-on-1 surface or 200 surface or 220 surface, no one can sure which electrode facet is the most active one. But many of theorists, including myself, rely on single crystal surface to explain the kinetics or different activity of this material for different reactions. So by suggesting those of theoretical mechanism, by measuring the Gibbs free energy following this reaction mechanism, we rely on this single crystalline material to fully understand this experimental measurement. So we are missing many of details like reconstruction or leaching effect during the experimental measurement, or grain boundary effect, or no one knows which surface is very active. So some of minor surface can be achieving very important role during the reaction. So some of theoretical groups are using so-called surface Puvet diagram scheme, which is draw a surface Puvet diagram-like diagram, which is just for considering the surface. So it varies the different adsorbate as a function of pH and electrode potential to browse the different forms of surface. Like at this region, the cerebral surface has to be pristine one, but at this potential and pH region, this must be covered from OH, like 1/6 monolayer. And at this potential region, this surface has to be covered by 1/3 OH hydroxide group. And at this potential and electrode potential and pH range, this surface has to be like oxygen substituted one. Even though it can consider some of these phenomena, it is quite restricted model since it never solves the reconstruction or leaching effect, since it just considers the surface, not the materials phases during the reaction. So we can find the importance of this effect from this example. So the Haramiro group measured the higher activity using this material, which is a strontium iridium oxide, and it was not known for active material for this reaction. However, they found out that after using this material and running the reaction over some day, they found some interesting phenomena happen that it accidentally shows some activity for this reaction, but it is even higher than this iridium oxide material, which is known as the active material, and they characterize that that material is fundamentally different from this material. So we can say that there must be some room in between this material and this material, which is active for or optimal material for this reaction is out of the reached out or reconstructed structure from this material, and no one knows the details yet about this. And another example is from the CO2 reduction reaction, and in this community it is well known, or it is thought about very important to achieve high value added product. So in this manner, the high valued product is so-called like not C1 product. So from CO2, we'd like to achieve C2 or C3 product, and this group found out and insist that this high valued product is actively produced on this surface defect or many of ill-defined structured surface, not from the kappa 100 like single crystal surface. So many of details are still unclear for this, and I'm thinking to figure out this phenomena is really important to understand this material and utilize this technology. Another challenge is in microscale atomic resolution understanding for this reaction is understanding kinetics. So let's see this experimental results again. It shows us the CO2 reduction product as a function of the applied potential. And based on this measurement, we often draw this energy diagram to understand the reaction mechanism following different electrode potential. So based on this CHE framework, I already told you that even though we control the macroscopic electrode potential, it is not from the electrode charging. So it is very important to apply electrical potential during the theoretical investigation. So let's again see how this computational electrode model works. So here I suggest you one of the example like CO2 to COH activation, CO2 to CO reduction step. So you can see that in this computation hydrogen electrode framework, every electron transfer step has to be occurred with proton transfer at the same time. So we call it as proton coupled electron transfer. So every step is occurred with this PCET step, and since this electron transfer has to be coupled with this proton transfer, we don't need to control the number of electrons during the simulation. I mean, we are not able to control number of electrons, so we cannot do the electrode charging. But because of these challenges and motivation, some of groups developed so-called implicit charging method. So they control the number of electrons at the electrode, but they compensate whole cell as neutral by using implicit solvation model to screen the charged electrode to make the cell whole neutral. And we can see and we can find the importance of this approach for the CO2 reduction reaction example. So actually, a kind of 10 or 15 years ago, the CO2 reduction reaction on the metal catalyst was believed as its reaction determining step as CO2 activation step to formate COH intermediate. But experimental group found out that this reaction is independent on pH, which means that this reaction determining step is not the proton coupled step. So this simulation shows that the CO2 reduction's reaction determining step is to activate the CO2 molecule into negatively charged CO2 form, which is the bent CO2, and they validate this experimental result using this implicit sorbation model by explicitly charging with the extra electron and using the implicit sorbation layer. But no one knows what this implicit sorbation layer, everyone is curious about how this implicit sorbation layer makes and helps this CO2 molecule absorb. And one of the experimental group and found out that the details of this one by using the explicit double layer model. So they hold the electrolyte component during the simulation to see that these cations in the electrolyte have the role to activate this CO2 molecule, and they found that this is the cation coupled electron transfer step to activate this CO2 molecule, and this is the reaction determining step of this reaction. And the key message that I like to mention here is it is very important to apply or explicitly making charging this interface with extra electron, and it depends on how we compensate it. But it is more experimentally measurable value. And the limitation of the current development was it is not the constant potential model, it was just constant charge model. So in experiment, the control parameter is not the charge, but the electrode potential. So to directly compare the experimental measurement and theoretical investigation, we would like to directly matching the control parameter. So from maybe around have developed different models of constant potential modeling, and the key idea is the most well-recognized model's idea is to control number of electrons during the simulation and find the optimal potential value by changing these extra electrons, and then use this converged value to find out the ultimate potential value that we want. So we can see the importance of this constant potential modeling with this CO2 reduction reaction example. So this CO2 reduction, CO2 activation step is well known that as the reaction determining step, and it is investigated, it can be investigated using this constant potential DFT method. So here you can see that by using this initial configuration like this bent CO2, by fixing this potential as this value, which is around minus 1.3, and hope this value is quite reasonable value for you then. So at this condition, it shows that this CO2 molecule is not activated. However, by using the stronger potential value is when the stronger potential is applied, like 1.8 volt, this CO2 molecule is activated, which means that this CO2 can be used as the CO2 reduction reaction at this potential range. This is actually not available from the old model, which was CHE model, since it is always coupled to the proton transfer at the same time. So we cannot see this potential control effect during this reaction, but since this proton has to be coupled every time. But by using this constant potential modeling, we can discuss this reaction mechanism more specifically, and it makes more sense and it is more solid model to validate experimental finding that the CO2 molecules reaction determining step is electron transfer to be a CO2 bent, and then the proton transfer step is followed by this step, and after that some more complicated reaction is proceeded to eventually make this product. So even though we found and we contributed many of findings to the development of this electrochemical technology, many of things are still unclear. The first one is the electron surface effect, like reconstructed or leaching out effect is unclear at constant potential, and the kinetics of this reaction at constant potential is still very unveiled. And furthermore, the explicit details like cation effect or some explicit sorption effect is not that clear at this constant potential case. So it motivates us to develop some constant potential model, and I'd like to show you here how my group is developing constant potential model to realize more reliable electrochemical interface model. So basically, my idea or our group's idea originated from the old development from Michael Sprigg's group in 1995, and Sprigg's group developed the constant potential model to be used as explicit sorption model, but mostly it was on the classical electrodynamics. So the potential was calculated from the Poisson equation, but the charge density or charge distribution was Gaussian charge-based distribution. So they can treat, or this model can treat, the constant potential with explicit sorption model over several thousands molecules. But the demerit of this model is this potential value is very unphysical. So the main reason is even though it makes sense to express the charge distribution of molecule as this classical manner, but let's say this material is silver or platinum, then understanding the electrons or electrodynamics with this classical expression is very challenging. So it makes this kind of very unphysical potential value. So this is our motivation, and I really appreciate this paper because the sky's the limit for this paper. I mean, the idea can be applied to any of theory, but the only thing is to remember is the computational time matters. So 30 years ago, since this model was developed 30 years ago, at that time, DFT calculation or quantum mechanical calculation was very challenging, even for small cluster of molecules or some unicell size of crystal. But now that we have very cool computational setups, we can try applying this method into DFT ranges. So one of my idea was, even though we can use the computational tools, highly developed computational tools, to express every atoms with the quantum mechanics is a nightmare. So I'd like to use kind of embedding theories to treat some part of atoms with the higher accuracy model or theory, and treat the others as low quality expression. So I conceived this idea to treat density function theory, to treat the electrode or quantum mechanically treated region as DFT, and the others as machine learning interatomic potential. And the merit of machine learning intertwined potential is its flexibility. So we can, in principle, apply this approach into any system. So one of the merit of classical force field, like in many of different approaches, the disadvantage of that model is not so flexible. I mean, in case of organic molecule, there must be some well-recognized model like OPLS AA model. And when it comes to metal electrode, it is recognized that some of the embedded EAM model is accurate, but we cannot use or we cannot treat or describe whole system into one single force field. So this is the merit of classical force field, but this kind of machine learning approach can do this. So it's because it just depends on what data is prepared. So even if, I mean, if we just prepare some enough database to accurately model the interface, whatever the model is not that important, and since it is very flexible to any system. So I conceived this scheme to treat this metal electrode as DFT and to treat this electrolyte component as machine learning intertwined potential. And one of challenges in the machine learning intertwined potential community is how to deal with these partial charges or long-range interactions. So basically, since this is the electrochemical system, to treat the electrostatic interaction is one of the important, or I can say that this is the most important thing. But in many of machine learning intertwined potential, treating this long-range interaction is very challenging. So I addressed it by decoupling or breaking it down into different regimes. I mean, even in the training step, our group break down this total data into different regime, which is short-range interaction and long-range interaction. And only the short-range interaction was trained for this machine learning intertwined potential. And long-range interaction, for example, Coulombic interaction, are separately considered during the calculation. And it was mostly dependent on the UR summation and grid-based integration or calculation with the external potential from the density function theory calculation at the electrode site. So on top of it, our group developed the implementation of theoretical potential stat, and it is mostly, I believe, consistent to the experimental concept of potential stat. So let's think about at time t, and at this moment, we are able to measure the converged electrostatic potential at this counter electrode and converged electrostatic potential at working electrode, and can measure the potential deviation, potential difference from this working electrode and counter electrode. So in principle, we have to use reference electrode to more accurately measure this electrode potential, but in this work, we use counter electrode as the reference electrode. Then let's say we are wondering what happens we control this potential value as phi 0. Then we need extra potential at this amount. So our group's idea is to apply another external potential to make these electrode particles more polarized with using this sigmoidal-like function. And by applying this extra sigmoidal external potential, we are able to control this phi walk above this one. Then we think it must be more closer to this potential value that we would like to see. And this is the result that we got. So we can well control this potential between the working electrode and counter electrode. So here you can see that without potential 0.5 value and 1.0 applied value and 0.0 value. First thing that I like to mention here is you can see that compared to the 0.0 volt, which is shown here as purple curve, this without potential curve, which is shown as the dotted blank line, shows you that it is fundamentally different from them. So in many of theoretical simulation, it is easy to say that this brute force MD simulation at certain surface is equivalent to the 0.0 potential condition, but I can say that this is totally different from that. So even though its averaging value can be approximated as 0, but it is easy to be biased at certain point. And thinking about most of ab initio MD time scale is less than 10 picosecond, some sort of results can be biased at certain potential values. So we can send some message, we can tell some message to theoretical community that these things are always very, this type of simulation must be very dangerous to say that. Another thing that I like to mention is this theoretical potential stat give us very nicely converged result, even though it has some deviation, but it is very physical phenomena that since this is the potential stat, so it always fluctuates a certain amount, and it is less than 0.25 volt, and it's very reasonable value, I believe, and we can well control this value around with difference of less than 0.25 volt. And the last message here I'd like to mention is the time scale is way longer than the brute force MD simulation from the solely using the DFT code. So it is just 1 day, just 5 day simulation result. So we can sample more than 100 picosecond within a week. So it is way larger and way longer simulation result compared to the single DFT calculation. So on top of it, we'd like to apply this methodology into different regimes. So we can apply this into various regimes like unstable, metastable, or non-equilibrium phenomena to explore many electrochemical problems within the system. So for this one of example that I like to mention is no one knows clearly the proton transfer step at the electrochemical interface. So I'm thinking about applying this methodology for this system or controlling the ion strength, pH for this phenomena. And we can also use this methodology into not just for the catalyst, but many of the electrochemical energy system, energy storage system like next generation batteries like sulfur battery, aqueous battery, or oxygen air battery system to explore some details of these mechanisms. And I believe we can figure out the details of this confined space-based electrochemistry, which is totally different from what the classical Poisson-Boltzmann model tests. And then we can also I'm thinking about applying this method into fast charging system like supercapacitor, or based on it to figure out the CO2 absorption system. And mostly I'd like to expand this methodology into many of systems to figure out the electrocatalyst mechanism. And ultimately, I'd like to merge this framework into photoactive material as well to figure out the photoelectrochemical systems. So I really appreciate every group member in Thames Group, and I appreciate your attention. Thank you. Sorry? Was it? So this is a very good question. So the main reason why this black curve shows high fluctuation than the other lines, and the simple reason is because it has no potential state. So once the molecular orientation starts to align some specific direction, it is easy to be collectively act together. So I mean, once this molecular orientation forms, it is hard to be returned to make this potential constant. And the role of theoretical potential state is helping this system to achieve the relatively stable electron potential or electrostatic potential. I admit that this model is exaggerating this phenomenon, but I really address this problem seriously. So this is why I chose this system. So it makes sense that if we increase the number of layers to see more many of experimentally matchable system, it is easy to be diluted, but I can say that in certain way that phenomena also could happen, but it's very good question, and I think we can compare more quantitatively by increasing the number of layers. Thank you.
Any questions? It's time.
Thank you, Jay. That was very interesting. You mentioned, I think, maybe I misunderstood you. You mentioned that you can only go in 250 millivolt steps in this approach, or did I misunderstand that? Can you go continuously in potential?
That's a very good question too. So the way how to control the potential value here is to set what potential we are curious about. So in principle, we can control it, but because of this fluctuation, it is hard to tell that the difference between 0.1 and 0.11. It is in principle possible, but there must be not so difference. And I believe in the experimental world, the kind of 10 millivolt, 10 millieV or 10 millivolt changes quite a lot. But in simulation and like this, so it is quite hard to see some difference between that applied potential condition. But in principle, it is possible to control and see the effect.
And is the noise the same as what you
Yeah.
That was, so that's the same, the noise is just, it
Exactly.
graphically displayed.
Exactly. So this is not kind of noise, but physically making sense one. Yeah.
Let's come Jay again.
Thanks.
I don't know.
This is for online.
Oh, it's one. Okay. Is it working?
Yes.
Okay. Hello, everyone. Ah. Okay, yeah. Sorry.
So next speaker is Ekaterina.
Yes, yes.
She's going to speak about accelerating catalytic discovery after site prediction and catalyst screening.
Yeah. Thank you very much for a good introduction and also for inviting me for this workshop. So let me introduce myself first. So I'm Ekaterina Tosheva. So far I'm a PhD candidate in King Abdullah University of Science and Technology. I'm working in Chaos Catalysis Center and under the supervision of Professor Luigi Cavallo. So today I would like to present some of my recent research when we're trying to combine the DFT and machine learning. So this work is mostly based on benchmarking graphical neural network for looking for the active site, and some further project that we also connect about the single atom catalyst, that we're curious what is the single atom catalyst is the best for different catalytic surfaces. All right, it's not working. So let me start from the really beginning. So as we know so far, the computational has the really long way. So the first paradigm is about empirical science. So we saw how people were just observing the nature and doing some observation of the nature law. So the second paradigm, when we started to employing some physical laws, some mechanics and thermodynamics. So far we can see some better representation of the nature. And the third paradigm, it starts to be the computational science, mostly the simulation. We can see that starts density functional theory and molecular dynamics. So, and the last one that has happened now in the 21st century, we can see big influence of the data-driven science. So here we can apply some artificial intelligence, statistic learning, and more other features. But so far, we couldn't mostly transfer all of DFT calculation to data science. So now we're actually in between of third and fourth paradigm. So at the moment, there is a lot of papers how we can see the combination of these two approaches. So usually we can see this on DFT calculation and some machine learning algorithm when we can see the feature engineering, model selection, model training, analysis prediction to build some Python codes when we can use exactly for the needed system. For exactly this example, they provided catalytic activity. So why is it important for us to use some machine learning? Firstly, I think the biggest reason it's because we need to reduce the computational time still DFT is taking so much CPU, and we can see even with starting from 200 atoms, if we are moving to more complicated surfaces, like connecting 2000 atoms, the DFT computational time increased like in 8 times. So machine learning still help us to make the calculation fast. So it's also really important for us as a catalyst people, because we are doing a lot of different DFT calculation for describing the needed surface and the molecules. So to reach this purpose, we also find the machine learning heterocomic potential really useful. So this is just one more example of how we can implement the machine learning. So we can see that there is a training sense, where is these different chemical compounds. In interpolation case, there is training data. In interpolation case, the meaning is the taste data. So in interpolation case, we can see that for the GW performance, machine learning is actually having a really good agreement. So, but when we are moving to the test set, the machine learning is showing some disagreement. But it's still okay, and it's still, we can prove that we can use it even for our catalytical purposes. So I'm moving closely to my research. So I'm using the catalytic reaction, and I'm absorbing a lot of different species. So as the machine learning interpolation in interatomic potential, I use the foundational MLIP. So one of them is CGNet, the second one is M3GNet, and the last one is orbital materials. So why we choose that one? So the first reason, when I start my research, there was one of the best MLIP that I saw, and it's actually really good for my purposes. So some of them MLIP wasn't that powerful, so I couldn't use it for doing the catalytic reactions. So we can see that CGNet is, it has the model size around 172 million parameters. It's what is also really important for us. It's publicly open space, so we can easily grab the potential and use it. So far, the stability, F1 score, and the other factors are not that good, because already time passed and so many different is much better so far. So, but what is also interesting in CGNet, so the Kate straight is the charge away embedding, so which is also can be really useful for the catalytic reactions. So, but mostly the purpose of this network is the structural relaxation and the composition diversity. So the next one is M3GNet. So it's also based on the materials project. That's also really important, as the CGNet is also based on materials project trajectory, but it's more filtered. So the data set's a little bit lower. Also the reason it's open source. So again, we can easily use it for our purposes. So the other parameters, if we can take a look, it's actually lower than compared with the CGNet, and it's also showing the lower performance. But we can see the combined performance score is actually a little bit higher than CGNet. So maybe the filtering data is also helping to increase this variation. And this method is based on three-body interaction. So we can also use it for our purposes, but this model is highly for the accuracy energy forces for discoveries of materials. So, and the last one, here is the option for the last version of the ORB. For my research, I used the previous one. So, but the new one is actually had also higher rate in the materials project MathBench discovery. So we can see now the second version was also open source, but now it's became more proprietary. So, but we can see this performance score and discovery is actually pretty high. So we are hoping that it will be even more available for do the thing that I'm planning to do. And its compact and robust generation, it's actually extremely fast, even compared with the CIGNet and 3GNet. The data result we can get even faster. And what is really good, because it's doing the geometry optimization, it can do the Monte Carlo and molecular dynamic simulations. So what exactly I'm working with? I'm working with the heterogeneous catalysis. And we can see the three main steps that we are doing during our process. The first one is adsorption. It's really important step for us because in this case, we are looking for the different configuration of the molecule attaching with the surface. So the heterogeneous catalysis happens between the solid state and gas, and we can see from the gas phase that all the molecule can adsorb on the surface in a completely different way. If the solid state has some vacancies, or if it has some alloy metals, so the system became even more complicated. So we need to include all of the possible position of the molecule on the surface. So during the surface reaction, of course, we can see the all intermediate state. And we need to calculate all of these steps really accurately because it depends how our pathway reaction will happen. So the last step is also important for us because we are investigating the desorption from the surface. It's a really important step, for example, for ammonia synthesis when we need to release ammonia several times. And it also can be challenging to desorb some species from the surface. So here is just one example of the catalytic reaction that I work with. So this is the most common is CO2 reduction. So CO2 reduction is mostly based on the two of them, reverse water gas shift reaction and Fischer-Tropsch synthesis. In this reaction, we can see that CO with the combination of the hydrogen, when it's react, it can desorb some water and produce some CO. With the following hydrogenation of CO, we can get some more complicated hydrocarbons and more water. So the catalyst surface is also really important for this reaction. So in this case, we can try to show the complexity of the structure that we are working with. So as I mentioned, all of this MLIP, they're based on the bulk surfaces. But in our scheme, we are mostly working with the surfaces. So it has the more atoms and it has more difficult structure in the surface. So in my idea for this work is how we can combine and increase the speed of our calculation. So I generated different system. So in my case, I'm using 5 oxide and 3 perovskite structures. Then we created the Python code, which is they're doing the scanning of the surface. So in general, we can get the adsorption energy of each point that we are doing the scanning. And based on this, we are creating potential energy scanning. And after that, the most important for us is how it's really matching with the WASP calculation. Because still in nowadays, we are, as the catalyst people, we are mostly trust the WASP data rather than some machine learning. So in this case, I will do explanation why we choose exactly these structures. So all of the structure wasn't chosen randomly. All of the structures, they're catalytically good for any type of the reaction. So most of them showing the good performance and really good efficiency in the different catalytic reactions. So in my case, yeah, as I mentioned, there is 3 perovskite and some oxide surfaces. So I will do more explanation how we are doing the mapping. So as I mentioned, there is the K reactants, which is CO, N2, and H, which also was chosen because it's really highly robust and it's more commonly molecules that we are using to predict the pathway reaction. So we place the CO in, just an example, for example, the CO, which we placed in around 2 angstrom above the surface. And for my code, we were using the step is 0.1. So we are moving according to the surface, like with the step 0.1 in X and Y direction. So in general, after this scanning, we can get like 81 point and see how it's really, what the absorption energy for each of these points. So based on this, you can see the result of these calculations. So in this case, it's still not working. Just a minute. Okay, sorry. So in this case, for most of the reactions, we can see actually it's quite similar to the VASP calculation. But we can see that slightly CNGnet and M3GNet is showing different side, but most of it's pretty accurate. If we can take for ORB version, it's actually pretty similar, and even the most noticeable for us, that even the energy range is the same. We can see slightly different from this, but it's not really, it's important for us, but so far we were not expecting that's good matching between the machine learning and VASP data. Sorry. So this is the example that we use for the titanium oxide. So this is the other K reactants that we check on the surface. So we can see that, for example, for N2, the molecule, the M3GNet, is showing even more weird result. But ORB is consistently good, and actually pretty good with the prediction and showing the same as the VASP data. For the hydrogen, we can see a little bit different story. So even the VASP calculation is really complicated to do the hydrogen absorption. And it also can be because we need to place hydrogen with the closer distance. But so far, we got this result, and we still even see some negative absorption. And it's also, if we are comparing, we can see the same position. So the next example is the perovskite. So it's more ordering person structure. So the CNGnet, M3GNet, and ORB, again showing really consistent result. But CNGnet and 3GNet is slightly showing the different absorption side, or even like deeper absorption, while the ORB is also giving some not that predictable result, but still we consider it as a good result. So we can see the consistency between CO and 2, and the hydrogen absorption, it's now happened the whole negative. We can see the disagreement between the MLIP and the VASP, but it's also we considering that actually the surface is highly preferable for the hydrogen absorption. So even we can see the whole range of the hydrogen is negative, which means it's really attracting for the hydrogen. So next, we did the parity plot to compare statistically how good is the matching between the MLIP and VASP. So in all of the cases, we can see that Maya is actually not that low. But for ORB, at least we have the 0.1. And we can see that even for the ORB case, all the data set is actually at least getting according to the line. So we still have even statistically agreement that ORB actually can be useful for our purposes. So the same situation we can see for N2 and hydrogen absorption. For the hydrogen absorption, surprisingly result even better. So now it's a little bit below the 0.1, which also we are quite satisfied. So here is the more details about the absolute error. So how we can see even the error for the CNGnet and 3GNet has the really big tail, and mediana is actually quite high. But if we are looking for the ORB, we can see consistently lower mediana, and the distribution of the error is actually pretty low. So what happens if we are going between the structure or compounds? Actually, we can see the same system. So we can see that actually aluminum oxide is quite getting the highest error, but it's still manageable because we still can see the consistent result between the VASP and, for example, ORB. So for all of the cases, we can see that ORB is actually constantly showing the pretty good result. So the last question that's really curious also for us, if the machine learning potential is showing exactly the same active sites that WASP is showing for us. Of course, the sum structure has some symmetry, and actually even if ORB or other MLIP showing the different position, it still can be the same active site. So this was really curious for us. So here we choose the other perovskite structure to see if it's really happening. And here we can see, if we are doing the matching of the structure, we actually can see that WASP is preferred to be in the hollow site. And we can see that actually ORB and CGNet is also showing close to this hollow site. So when we will do the full optimization, it actually can be the same active site. And even the perfect result we can see for the indium oxide. So when we are choosing the lowest energy absorption, ORB and WAS showing exactly the same site. So we are really satisfied with this result, and that's why we decided to use ORB for our following project, where we will decrease the amount of calculation that we need to do by DFT. So the next is single atom catalyst, and we can easily do the scanning of the surface, not doing a lot of the calculation to place the needed single atoms on the right place, but just the running ORB to find this active site and continue machine learning investigation of single atom catalyst. So why we are really interested for the single atom catalyst? Because it's really showing the better stability of the structure. If we're adding any type of the single atom catalyst, it can increase the activity of the structure, it can perform the better selectivity and efficiency. But also is really good that for the experimentalist, they can spend less money to place just single atom catalysts compared with the other nanoparticles or the metal absorption. So for this project, we choose the 50 different atomic elements that we would like to place on the surface. So most of them, of course, it's transition metals, and most of this data, it will be based on this. So, but for this, we decided to go a little bit in a different way. So rather than doing also the perovskite, we decided just to focus on the oxide surfaces and to increase this data set with the 5 that's already been used for the previous work. We added 5 more structures, which is also really good in catalysis and most commonly used for the catalytic reactions. So with these 10 structures, what we were doing, as I mentioned already, like we are placing single atom catalyst and we're running this through the code that's been created. So after the mapping, we understand where is the lowest absorption energy can be, and we're placing this single atom exactly on this active site. Then, anyway, we are running the DFT calculation on this predicted single atom catalyst, because we really need the accurate data, because after this, we need to build some machine learning to predict what is the best single atom catalyst. So that's why we are using some DFT features. So in this case, we're providing whole DFT calculation, and we need to take some systematic features and some electronic features, and with data generated that we use materials project, we also can take some atomic features of the single atom catalyst and actually see what is the biggest impact from these features. So what does really matter, the structure or the single atom in general? So to reach this, we checked the different machine learning. So we went through the several of them. So here we can see not actually good predicted, because RMS, yeah, it's pretty high, and R square is just in the range of 0.7 to 0.6, which not that good. Usually it should be close to the 1, so we are expecting more closer to this number. But we can see that distribution of the points is actually pretty close to the line. So in this case, we provide even more machine learning. So we are still trying to find the best one. So out of this one, we can see that it's actually gradient boosting, showing the most result, the closest, the highest result. So R square is 0.8. So we choose this model as the model that we would like to do the following analysis. So the same results we can see that's for the error analysis, as I mentioned, like for the R square, it's showing the highest result, and for the root mean square, it's also showing the lowest one. So out of more models, we still can see that gradient boosting, it's consistently showing the better prediction. So they also, that I mentioned, important for us to see what the important feature that we can see. So in case of the gradient boosting, it shows us that the one best is total magnetization of the structure. The top three is also in the second place element valence and actually the band gap. The band gap of the structure, so we can see that most of the important features coming from the single atom catalyst, but also from the catalytic properties of the structure. So we also did analysis of the ML prediction with the taste data to see, because our common idea is to use some structure which is not in the list. So if the, for example, experimentalist can easily decide like, okay, I want to put this single atom catalyst on these oxide surfaces, like what oxide surfaces and what single atom catalyst should I use. So in this case, we need some test data on the structure which is not in the list. And also, where is some single atom catalysts are not in the list. So we provide this correlation. So we do the one more machine learning prediction to see if we can really do this prediction. But so far, it's actually, this project is still ongoing. So all of these results are not the latest one. So, and here we actually can see that predicted absorption energy is not that good matching with the DFT result that we got. But for example, for the platinum, we can see that absorption energy is actually at least closer compared with the other numbers. So in this case, even for this step, we are expecting better R square and lowest Maya. So to reach this, it's also a future direction. So we also thinking maybe we should again increase the oxide. And we need deeper feature analysis. So maybe some of the analyses are not getting that good impact. So we need to get rid of them. And we need better DFT validation. And so the last part is also need to be modified. So this is the, in general, was the workflow, how we're seeing our single atom catalyst machine learning approach. So this is the end. I would like to thank you to my professor, Luigi Cavallo, and my colleague, Dr. Rafi Ahmad, that's been trying to make this project together, my Catalyst Center, and of course, Supercomputer Core Lab for providing the computational resources. Thank you very much.
Prediction part of the lower energies are more off from the R squared value than the others. Do you know why is that?
So even the range of the absorption energy, it's not really predictable, the -10. So the more realistic results, it should be, I think, -6. So I think it's big disadvantages that's shown here. So I think the absorption energy range also need to be tuned so we can better data selection on this. Yes, but of course, like if you are finding some active site, but also that's really influenced, it's how the molecule is absorbing on the surface. So which position or which geometry it's placing on. So I think it also can be really important to reach the lowest minimum.
Is it possible to deal with like defects?
Yes, yes. So the common idea of this mapping, it's because mostly, even like because I'm taking a lot of the experimentalist work, their surfaces are not ideal. It's contain a lot of defects or allowing species. So this is also helping us to see, for example, if it's more preferable to stay in the vacancy or somewhere else. So yes, this mapping it helps us to do this.
It's a very nice talk, and I wonder your impression or intuition. I mean, those models are basically not for investigating some surface phenomena. They're supposed to be used in bulk materials property calculation. But you managed to use this for your research. So I wonder your thinking. So do you think those models are quite good for doing those catalysis stuff, or do you think we need some other models like open catalyst models or like that?
So yeah, it's a really good question. That's how we started to think, and that was the biggest worry, because yes, as I mentioned, all of this NLP was based on the bulk. So, but we were curious, maybe it might work because we can see that it's actually can still give us prediction of the total energy. And since we are doing the absorption energy prediction, it's actually the more absolute value. So if the absolute value is matching with the VASP result, we are more than satisfied of this result because that's the most showing parameters for us. So in this case, I think it's still getting better, and I think the Oribin now actually start to provide some more data sets. So now we can even use it for like more bigger structure. So I think it's not ideal, but I think it's pretty commonly we can start to use it for these purposes. Thank you. Oh.
Thanks, Kanta.
Next speaker is Ben. He's going to talk about tool-guided electrocatalysis discovery using high-throughput spectroscopy.
Thank you. Hi everyone, I'm Benjamin Moss. I'm a Lindemann Fellow at Caltech and an incoming lecturer at University College London. I'd like to talk a little bit about some work of things that don't usually go together, which is operando spectroscopy, which is the study of materials in situ, and high-throughput approaches. So I'm sure you're all aware as motivation, these machine learning algorithms are really starting to accelerate like all levels of the drug discovery pipeline. There's really a measurable impact in how machine learning is improving this part of the field. And these sorts of algorithms, things like AlphaFold, these diffusion models are based on deep learning or deep chemical insight on a vast scale. I'd encourage you to look at protein structural databases that biologists have at their fingertips, which contain really gold standard crystallographic and cryo-electron microscopic information. kind of where the protein is expressed in the cell. All of this is done in a very standardized format, the sequencing, the errors associated with sequencing the mutations. This is really a level, a kind of real deep level of chemical insight. If we think now about machine learning for materials discovery, we have not yet seen a acceleration in discovery, despite some of the claims that have been made. I think there's perhaps two reasons for this. The first, of course, is that we often work with devices that utilize nanoscale interfaces, and these interfaces are inherently harder to characterize, they are harder to predict, they are harder to understand. But I think perhaps the larger problem is that we've heard a lot about restructuring and the difficulties in both predicting that and measuring it. And perhaps the most difficult problem of all is these interfaces often only evolve under operational conditions, and the nature of the operational conditions can drastically change the nature of the interface. So one might be, in the literature, you could commonly find that people are giving the same name to the same apparent material to later find that the interface is drastically different. So operando the interface data, the data that describes these interfaces, is rare versus bulk data. And so I think it's reasonable to say that we lack a commensurate level of chemical insight. My interest in the case study I'd like to give you is the oxygen evolution reaction. I won't spill too much, waste too many words about it, but it's obviously it needs effective catalysis, and the only commercialized catalyst that we have for this is one of the scarcest elements on the planet. To give you an idea about how scarce iridium is for PEM electrolysis, it would require 27 years to have 1 terawatt of global iridium production, to have 1 terawatt of electrolysis capacity. So in the high throughput experimentation group where I work at Caltech, we use high throughput combinatorial techniques such as inkjet printing and 6-target combinatorial sputtering to produce different libraries, either printed libraries or gradient compositional libraries on plates. And we have very, very large numbers of compositions. And then we use, most commonly use these microfluidic tools, the so-called scanning droplet cell, to assay their performance. If you combine this with high throughput X-ray fluorescence, you create these compositional maps of performance. So in this case, this is the experimental overpotential for oxygen evolution. And so you get these maps of different compositions. 200,000 plus compositions have so far been tested in the group, but no iridium replacement has been found. And I'm sure you're all aware of the scale of the problem is essentially the curse of dimensionality. So if you think about the kind of combinations, as the simplex of possible combinations, as that you increase the number of elements, the number of combinations increases, the volume of the simplex increases up to some limit. So essentially, this is the curse of dimensionality. So you have more elements means more dimensions. If you think about 4-element combinations, to do an extremely coarse sampling of this space, 10% compositional increments, which is, I think you would agree, completely different. You can have 1% compositional change, which is very drastic, would require 1.5 million combinations. So we need both scale agreements. But I'm missing something in this slide, which is the fundamental importance of the microenvironment. Right? The microenvironment drastically affects things. So we could assay this entire compositional space with wrong microenvironment parameters and find only failures in this space. So really this is an exponentially larger space if you think about the possible combinations of electrolyte. In the high throughput experimentation lab, we have some tools available to us to help us learn about materials. Unlike in common chemistry labs, we don't consider a sample to be a sample in a box, but rather a history of all of the processes that have happened to that sample and with associated metadata. So for example, a sample is not a sample. The processes that can happen to a sample are like state-changing samples, like annealing, state-changing processes like annealing, and associated metadata. Things that are assumed not to change the state, like XRD. And these processes can be associated with data, process data, like a phase map, for example, compositional phase map. And we can also measure performance, which is always assumed to be state changing, and collect this process performance map as well. The reason I'm telling you this is that it tells us something fundamental about learning. If we take a cerium, iron, manganese, nickel quaternary space, so a tetrahedron, unfold that tetrahedron, so unfold the outer layer to get this area, then the inner layer, and then the inmost layer, you have this map of overpotential. If you try to take any common supervised learning algorithm, so take XGBoost, for example, and try and learn performance from composition, you fail. You cannot do it. If you, however, include the process metadata back into that comparison, you do an okay job. You start to be able to resolve broad trends. And this is essentially a machine learning equivalent of saying that composition is a bulk property. It contains no interfacial whatsoever, so there is no way of learning from composition alone. The history of a sample, from an experimental perspective, is a recipe to make an interface. So one can expect that if you have the history, you know the route to the interface. So history improves learning, but just like in standard experimental science, you might know how to make a performant interface, but you might have no idea why it works, and you have no way of learning. So you don't have a physical theory to help you transfer that knowledge. So for that, we of course need descriptors. Descriptors have already been discussed. Are physical parameters that should correlate with performance. There are many. Jay's really nicely described them and kind of talked about them. And one of them, of course, is the oxygen binding energy for the OER, which follows this Sabatier relation. But if we actually look at some experimental data rather than theoretical data, you see this enormous amount of scatter. So for this descriptor, enormous amount of scatter. And if you actually remove these 2 points, this trend almost entirely vanishes. And I think what this really is suggesting is that, of course, an obvious thing, which is that binding energy is an incomplete theory of activity. It would be quite surprising for the entire theory of electrocatalysts to fold into a one-dimensional theory. And there are many, many reasons, other parameters that might also describe activity. So a couple that I would like to talk about today are these kind of non-covalent interactions that occur in the at the interface, which can be modulated by the coverage of different intermediates. So these, I'll just generally speaking call them interactions. The origin of those is slightly unclear. There can be many, but this is a very non-exhaustive list. 2 dimensions is only one step up in complexity. And although I will be talking about 2 dimensions today, you could imagine a lot of other things, like, for example, conductivity. Because if your material is too thick and is insulating, it doesn't matter how active it is in all other ways. You lose all your potential before you reach the surface. So we can experimentally extract descriptors, but we mostly need to do that in single crystal model systems. So you can make, using something like PLD, a single crystal facet, epitaxially grow a single crystal facet that's well defined. There is some level of assumption in your hoping that your surface doesn't immediately restructure when it hits the electrolyte, which is commonly seen. This is a scary assumption in a way, because if you look at STEM, you introduce carbon monoxide or water to a well-defined surface in the gas phase, and the surface immediately restructures. But let's not worry about it and say that the surface is well-defined. It's not changing very much, so we could make, for example, a 110 surface of iridium oxide, and we can measure the waves of pseudocapacitive charge that the surface undergoes, and because we know what the surface is, we can make very good guesses about what these waves might be. And so, if we know the charge as a function of potential, well, that's just the integral of the current times the scan rate. So if we know that, we can calculate a thermodynamic parameter called the degree of completion. The degree of completion in simple cases of A goes to B plus an electron is the same as the coverage. It doesn't always have to be. You might imagine a case where a reaction of A goes to 0.1 B. In that case, you'd have a coverage of 0.1 of your surface, but the reaction would have completed 100%, even at 100% completion. But we can imagine that this is in some ways analogous, is a thermodynamic parameter analogous to coverage. You can rearrange the Nernst equation and, in the form of this degree of completion, and so you can extract the binding energy. And also, if you have a simple toy system, a two-dimensional toy system, localized interactions, you derive what's called the Frumpkin adsorption isotherm, which is just a Nernst equation with this extra, you can think of it as a first-order perturbation, and just a kind of squinting at the entire system and saying, okay, if I increase my coverage by a certain amount of this intermediate, and it destabilizes the local microenvironment by a certain amount, let's say it's a linear destabilization. So you have this linear toy system destabilization. This is very nice. You can extract all these parameters, but unfortunately, this does not represent deployable materials, and these studies take about 4 to 5 years from inception to completion to publication. So they are really not scalable. And there's a bit of a problem, which is that when you look at a real, more deployable material like an amorphous iridium oxide thin film, so Jay talked about the strontium iridiate. The strontium iridiate typically forms a material with very limited long-range order and some structure in its middle range order. So these kinds of materials are quite hard to, it cannot be analyzed by this approach. So perhaps an interesting goal would be is if we could scale up the potential of operando spectroscopies to take into a high throughput workflow in which we still work on these combinatorial spaces, these large combinatorial spaces of compositions. So we have a phase composition map, but we also have performance maps, but we are also able to extract at a similar scale things like binding, things like these interactions, the nature of the local water structure and the intermediate identity. This would be the kind of long-term goal that would be good. The kind of data that this would produce could, in principle, be seen as a deep chemical insight on a scale. This would be something closer to a gold standard, as it would allow us to distinguish apparently similar interfaces. Oh, that's a bit blurry. That's supposed to be a machine learning icon. But hopefully this would allow us to get better materials. So perhaps there's a destination here, but not a route. Oh, I've got this. So I'd like to just briefly, before talking about the destination to get there, I'd like to talk about some challenges and difficulties and general problems in our assumptions, as this has maybe got a bit more of a fundamental take on it, this series. And there are kind of 4 big assumptions that we tend to struggle with, whether we're theorists or experimentalists. The first is active site homogeneity. The classic Ertl kind of literature of heterogeneous catalysis suggests that there's always subpopulations of sites that are exponentially more active. And almost all of the activity tends to flow through these subpopulations. We tend to have to avoid that assumption in electric catalysis. There is some literature which shows these subpopulations, and the hope tends to be that in complex materials, the material is sufficiently disordered that these active populations represent a large kind of proportion of the total number of sites. And so in some way we can hope to make these homogeneity assumptions work for us. This is a weakness of operando spectroscopy, because if we have a very small number of fraction of active sites, only a microscopy will be able to detect these. Dynamic surface evolution. All our materials rapidly restructure. If you consider platinum 111, I think, after a single cycle, there is rapid and reversible restructuring. So these single crystal studies seem to suggest very complex behavior that we haven't yet got a very strong handle on. Spectator intermediates. This is not a problem so much for DFT people in terms of what you calculate, but it is a problem in terms of what experimentalists say to you. Because a classic problem in the literature is they measure by Raman, for example, an intermediate. But if that intermediate has an extremely low turnover frequency, it can exist in a very high concentration, a high coverage. So the gold standard of proof is that an intermediate must exist at sufficient concentration and turn over at a sufficient rate to drive the experimentally measured current. So without those two parameters, you don't have enough information to prove that your intermediate is important, and you can end up going in a strange direction. The kind of final thing I want to talk about is the origin of changes in the free energy of rate limiting intermediates. So there's this classic picture of like the market, essentially, but the Volmer theory is derived from more or less the Marcus theory of electron transfer. So for this outer sphere electron transfer of an electrode, essentially what we're controlling is the free energy of that intermediate, right? Via the electron. So we have this kind of behavior of like activation energies that are scaling essentially by Polanyi scaling, if that's familiar with people. The term of this is Polanyi scaling of the activation energy due to the change in potential. But there is actually some reason to believe that this change, that the potentials of some rate determining steps in electric catalysis are not controlled by potential. So this was a big paper in about 2021, I think, by Travis Jones as well as Dieter Tischner. They found, Simone did these calculations of time-dependent DFT, so very, very expensive calculations. For iridium 110 at least, what they found is that the rate determining step involved two sites, a bridging oxygen site existing at 100% coverage at these potentials, and a coordinatively unsaturated terminal site. And what happens in the RDS is OOH is formed here, but the electron transfers over to here. So no proton, or the proton and the electron travel. So you make OH here and you make OOH here. There's no proton or electron transfer across this interface, so it is not electrically controlled in the rate determining step. And yet you see a Tafel slope. There is a measurable Tafel slope. So what they found is that these coverage-dependent interactions, they claim via the water network, but I think the jury is very much out on that. These coverage-dependent interactions are linearly scale with coverage. The activation energy linearly scales with coverage. The reason for that is that the coverage is linearly affecting through that R theta parameter the free energy of the rate limiting intermediate, and so is scaling with the coverage. So that's just to say this equation. Basically, EA is proportional to alpha R theta. So what that means is you end up with something that looks functionally identical to the Butler-Volmer equation, but with a different physical origin. In this case, this A theta is coming from these coverage-dependent interactions, the destabilization of the intermediate with increased coverage. This has a lot of consequence for simulation and Tafel analysis, because it appears that the barrier, at least in the kinetic regime, is strongly modulated by the microenvironment and the coverage of the intermediate, which we struggle to access. But also Tafel analysis, right? Because this is probably the most commonly used set of equations in electrochemistry. You have a pre-equilibrium and then a rate determining step. But this has two problems. In this case, this has been done a lot for iridium oxide, and there's two problems. The first is the form of this equation, right? The second is the coverage, because the coverage, because of that R theta term, doesn't behave according to the Langmuir isotherm, which is the Nernst equation. So you have a non-Nernstian coverage and you have an activation energy, which is varying for a different reason. So although this equation will work because it has the right functional form, everything gets parameterized in the wrong way, so you end up with the wrong conclusions. So I think, going back to high throughput spectroscopy, I think operando UV-Vis is a really good tool to solve some of these problems, and I'll explain why. I think the thing that we're converging on in the literature about iridium oxide, its surfaces, is it has three distinct redox processes. So you pull a proton and an electron first off this terminal site, then off this bridging site, and then off the terminal site again, and you generate something that's actually got O1 minus character at the end, and this is the rate limiting intermediate. If you want to do gold standard experiments, you go to a beamline and you'll do some in situ iridium LEDge spectroscopy. And if you drive the system in potential up and down these different processes, then what you find is the first process is tracked and the second process is tracked, but the third process is completely invisible. So what that means is you have to go to another beamline end station and do a really fiendishly difficult experiment, which is an in situ oxygen K-edge experiment. So that's the X-ray absorption of oxygen K of a surface submerged in oxygen K liquid. So it's very, very difficult to do. But if you can do it, we were able to, what you see is the first process is not tracked, the second process is slightly tracked, but the third is strongly tracked. So you can resolve these processes, but you could also much, much more easily resolve them by taking any benchtop UV-Vis spectrometer, dialing it into kinetic mode at 600 nanometers, and driving the system through all of these potentials. So you can really clearly see all of these, all three on any UV-Vis spectrometer. And from a theoretical perspective, that's because these UV-Vis transitions are from a continuum of states to a continuum of states. So there's such a mess of transitions involved in this that UV-Vis ends up becoming an extremely sensitive probe of oxidation change. The challenge, of course, is that because there's this mess of transitions, the identity, the chemical identity information is entirely lost. The reason for that is that these changes in absorption are not related to extinction coefficients, but rather changes in extinction. So imagine if you have A going to B, what you measure is the differential extinction coefficient of A and B. The reason for that is that in typical university UV-Vis experiments, you choose a subset of model systems where you have distinct extinction coefficients, so reactants and products. And as the products, reactants and products, and as the products are consumed, you lose absorption here and gain absorption the reactants are consumed, you lose reactant absorption, you gain product absorption. But in real materials, these extinction coefficients entirely overlap. They're extremely broadened. And so you measure differential extinction. See, what is to say is you measure a process spectrum, a process fingerprint, not a fingerprint of a reactant or a product. You don't measure a state fingerprint. So this is a powerful technique, but it does have some limitations. But I think it's a really, really good use case because what you can do is collect, in principle, you can collect spectra much quicker. An X-ray absorption spectrum can take half an hour to acquire, but as I'll discuss in a moment, UV-Vis spectra can be acquired in milliseconds with high resolution. If you can collect a spectrum with very, very high potential density, every millivolt, you end up with this kind of matrix here of the relative change in absorption versus the resting material. And what that is just driving the material through its intermediates. And what you can imagine is that this this relative absorbance matrix is the product of a evolutionary matrix and a and those normalized process spectra matrix. So imagine if you have a process spectrum, it can be scaled by any scalar to give you an idea of how much stuff there is. But of course, the scale of that spectrum is not important. So if we normalize it to 1, we have some kind of hold on the shape of the spectrum. So you have these evolutionary matrices and these process matrix, but this evolutionary matrix, as it turns out, must be proportional to partial charge. So it must be normalized in exactly the same way as we discussed earlier. So this is a direct measurement of this coverage. Again, we can pull out, if we can do this factorization, we can pull out binding and interaction, but we can do so for much, much more complex systems and in real time. And there's a very nice property, and this is a generalizable property of operando spectra, is that in general, the thermodynamic properties have logistic sigmoid, they behave according to logistic sigmoids. And so if you can take, I'll go back a step. The difficulty rate, of course, of this approach is, how do you factorize this matrix? There's literally thousands of degenerate solutions, and this is a very high dimensional space, right? But the kind of way you can do that is by taking derivatives, because if you take the derivative of this matrix, right, the evolutionary component, the potential derivative, must come from this differential evolution now, and that behaves like a Gaussian Lorentzian type thing. So what you end up with is these semi-sparse matrices that give you in specific points the different normalized process spectra. So once you have these normalized process spectra, you can then go back to the original matrix and back out the true evolution. But there's a catch. So there's another way of saying this, which is that this normalized derivative matrix is susceptible to clustering. It's susceptible to unsupervised learning. So you can find these clusters of normalized process spectra where things are not changing. So you see how this is not changing here, and actually it turns out right up here. There's a problem, of course, which is that a lot of common UV-Vis spectra setups waste a lot of light, and they acquire extremely slowly. And so that means that you can't acquire this kind of matrix because you don't have the resolution, nor do you have the density to take derivatives. So I think there's a kind of a general lesson here that perhaps there is a generalized need to integrate advances in detection, in how we analyze data, and to kind of take advantage of advances in open source environments to integrate technological advances into operando spectroscopy. And here's just a simple kind of schematic of a system I built quite a long time ago that utilized some optics advances and some simple automation and to measure, and some detection advances to measure high resolution spectra. Again, going back to the iridium oxide, this is a real-time spectrum of the iridium oxide. So you have these current waves here. You see these current waves, and this is the relative absorption from the start. And you see you get this change, but the normalized derivative of this is clustered. And as you move past this current wave onto the next one, it diverges and then starts to converge as this wave gives up and a new process takes over here. So now it's convergent. And then another process is going to take over in a moment, and it's going to diverge and then cluster to that new process spectrum here. And that process is rate limiting, so just is the generation of the rate limiting intermediate. So just before this, the OER takes off and you see a lot of bubbles. So we were able to take this and apply this to this amorphous iridium oxide, and essentially we knew that we could get these normalized derivative spectra, so we were able to bundle everything into fitting coefficients and backfit out this the dynamics. And if you do some extra experiments, you can actually find the coefficients that gives charge from beta. So you can extract partial charges, and from these partial charges, you can completely reconstruct the measured current. So you reconstruct the measured current, and from that you can be confident that the final thing that you see, turns out, is the rate limiting intermediate, and so you have a means of measuring binding and electrolyte interaction. And we did that, and we found that what happens at fixed potential is that these coverage-dependent interactions, you have some finite coverage. And so for a series of different types of iridium oxide, we found that you move off this kind of 1D volcano and onto these much, much more complex surfaces. And that really helped us explain a little bit more, or slightly more accurately, the performance of these materials. Now you might ask, this volcano predicts a very large modulation in activity that can happen in the strong binding region. So you can have some materials that should truly suck, they should be terrible, but there should be a way to make them quite good. So is that possible? And it turns out that you can, in fact, do that. If you take iridium oxide and you put it in alkaline pH, you see all these waves change, but actually you get more or less the same performance. And it turns out if you do exactly the same analysis again, you find that you have an extremely strongly bound intermediate that's generated very early on, very early potentials, and it's almost completely inactive, it doesn't turn over. But then as you increase its coverage, there are extremely strong interactions which appear to drive it up the volcano. So at potentials, these overpotentials where things are starting to saturate, where coverages are high, you have a strong interaction here, so you have commensurate activity to iridium oxide, and so you end up with commensurate currents because you have commensurate turnover and commensurate populations. We speculate that these interactions might be due to the water network. We did some in situ differential surface enhanced IR spectroscopy with Yu Katayama in Osaka. And what we found is that there is indeed a change in a region associated with asymmetric water stretches. These are associated with kind of having a big ion there disrupting the surface. So what you can imagine, or what we speculated, is that these large ions, as you move them, as you start to push them in and out of the double layer, essentially, or in and out of the kind of interfacial region, they more strongly modulate the effect of they more strongly modulate the water network. And so you have these very strongly dependent coverage-dependent interactions. So I think this suggests that interactions can strongly modulate activity and that we can extract these descriptors in complex materials. So then the next question is, can it be done at scale? So that's really my work at Caltech, which is designing this instrument called HiSpec, which is, I think, the first high-throughput operando electrochemical screening system. It involves some additional improvements in understanding how detectors work, how to do good detection in the high dynamic range region. You can essentially raster across with an XYZ stage. And we did a lot of work with Ryan, the engineer of HTE, on designing this 3D printed flow-controlled scanning touch cell. So this is a gasket cell with a 2 millimeter diameter contact to this plate. And we have a 3 electrode configuration in a millimeter diameter volume, essentially, very small volume. And then we just raster across this library. There are some connections to open source software here, libraries, because if you're doing a high throughput campaign, you're working with very large amounts of data on precious samples, and you need to be able to first reliably run your experiments, and also they must be kind of flexible and nimble. So the way we work in HTE is that we don't design monolithic code, but rather design these provenance embedded experiments using web servers. So what this essentially means is, instead of having running code of everything, each component of an experiment, so you might have a potentiostat, you might have a detector, it has its API embedded in a web server, a fast API web server. And what that means is that each thing that experiment can do is called an action, and it just becomes a HTTP endpoint on the web server. And the reason this is reliable is you can take advantage of very, very nice packages that are extremely well tested and extremely stable to design an experiment as just a list of actions. And this is nice because you can really easily deeply embed process data and calculate things and upload them and produce kind of nice quality data deeply embedded with metadata. So an experiment is scalable because an experiment is a sequence is just a list of experiments, and a high throughput campaign becomes a list of sequences. So it's very scalable and simple. This is the final instrument, and maybe it's easier to show a small video of how everything works. So the workflow, just to remind you, begins with 6-target combinatorial sputtering. So we sputter combinatorial plates up here, and then what we do is we do high throughput X-ray fluorescence and high throughput X-ray diffraction on a map of 256 spots on that plate separated by a few millimeters. So you get these nice combinatorial libraries after annealing at 700 degrees. This is the cell being lowered onto the system. So you can see all the spots where the samples made contact before. And this is an idea of the workflow. So now this is a web server, right? You can see this web server, the cell's filling up now, it's purging. And it measures open circuit, it does an impedance spectrum, and then there's some other things that happens that I'm not showing here, but using all these parameters, it figures out how to do a cyclovoltammogram. So it does a cyclovoltammogram, and it's collecting spectra simultaneously during this experiment at every 10 milliseconds. So once it's done, it purges the electrolyte, and it moves the plate to a new spot, reconnects, everything goes again. Before I talk to you about data, I'd like to talk a little bit about the hype in this field, in autonomous chemistry particularly, experimental autonomous chemistry, because there have been papers recently that have either made claims that have subsequently proven to be premature, or made claims that have been, as it turned out, have been false and been fabricated. And so one might imagine that there's this kind of curve of hype that might, of a kind of bursting bubble of people becoming very, very excited and then rapidly disillusioned and not wanting to use machine learning tools at all and not wanting to fund that. But these tools are useful. They have definite uses as long as we can prove that. There's been some really good corrective discussion, but I think as a field we're actually quite good at proving. We know how to prove what we do, what we do works, right? Because in solar cells we have this beautiful benchmarking, and we also have this in batteries and electrocatalysis. And if you cannot prove that your process benchmarks a known standard, then it's unlikely that your claimed advance is valid. And most people agree that this is quite standard in journals now. So with that, I'd like to show you a benchmark campaign. This is a 10-centimeter round of iridium oxide with identical thickness and identical composition throughout. So we sampled it in 100 places randomly. So it's randomly sampled in 100 places. We performed 1,000 spectral electrochemistry experiments consisting of 5,000 distinct electrochemical measurements. That consisted of 20,000 distinct actions over 4 continuous days of operation. And as an experimentalist, the thing you might want to ask, right, is, well, is the cell resistance any good, right? There's this thing, the solution resistance. So what you can imagine is if you make contact with your cell and there's a dirty great bubble sitting on top of your electrode, you have a massive resistance. You can't measure anything, right? So you need to reliably make good cell resistance contacts, essentially. And you can see that generally speaking, we are able to make a reliable cell resistance with a standard deviation of 14 ohms. This resistance is higher than a normal electrochemical cell, and the reason for that is that we are working on a 2-millimeter aperture, and that is embedded on a 10-centimeter round. So there's a resistance cost of just getting across the plate and then getting up to the cell. So here's some cyclovoltammograms, and they look really nice. You can then benchmark this, right? You can benchmark the overpotential against sputtered iridium oxide films, right? And you can see that this matches very well to the literature benchmark. But so far, this hasn't shown anything new. This essentially says that I have a valid electrochemical process and not much more. But this was also collecting spectra. So we can randomly, what these are the spectra on a linear sweep from open circuit to the maximum. And you collect the differential absorption versus open circuit. So we can randomly choose 30 spectra. And because this iridium oxide we've measured previously, we can compare this iridium oxide to the benchmark. And you can see that it's approximately similar in maximum identity. It's just 18 to 16, peak at 700, dip at 500. So that looks quite good. As it turns out, the advances in optics detection have led to a 10-fold increase in sensitivity whilst preserving a 1,000-fold increase in throughput. Depending on how you define success, we succeed roughly 80% of the time. So in general, this is quite reliable. So what this means is we have high-resolution data to take derivatives, and we don't lose too many in our pipeline. So we've got very, very statistically significant numbers of spectra with enough resolution to take derivatives. And what this means is we can start clustering on these normalized derivative spectra here and finding the regions in which they converge, and then pushing these into a pipeline that my collaborator, KK Lin, has really worked hard to develop, helped me develop as well, which is called BERU, which is bootstrapped estimation of R and U. And essentially what it does is it takes the relative absorption, get the derivative, normalize those derivative spectra, and then it initializes a bunch of hierarchical density-based clustering algorithms. It then figures out which one is the best, which one gives essentially the best fit, and then uses that to initialize a minimizer, a local minimizer. And that minimizer, once we've got this good estimation, basically the way it works is it takes these dynamics, fixes the spectra, because the problem is very large. It's minimum, I proved actually with Zhenshu that helped me prove that the minimum dimensionality of this problem is, for 3 components, is 9 dimensions. So it's still very high. Even in the 9-dimensional space, you can't just use like a Bayesian optimizer. If the Bayesian optimizer dies, you actually do better to randomly sample for solutions than to use things like that. So instead what we did is we fixed half the dimensions, optimized for dynamics, then fixed dynamics and optimized spectra. So this is called alternating regression. This is an MCR, AR, multi-component regression, alternating regression. And in this case, it's physically informed because the dynamics have to obey certain behaviors. So this is how it looks when it works. So you start off with a good guess of spectra, you get a guess of dynamics, you improve your spectra, you improve your dynamics, so on and so forth. So what ultimately the hope is that you get the binding energy and interactions of the strength of the rate-limiting intermediate. So if you do that, is it? It's frozen. Just give it a second. I think it's going to go. I hope it's going to go. It's just okay. So if you do that, what you find, what you can do is benchmark. Place all of the previous plots now on this three-dimensional volcano that I'm showing here. So this is the same as those more complex spaces, but it's kind of unpacked. So what you see on the bottom is the binding energy, and this dashed line is the one-dimensional volcano, the classic volcano. So this is the binding energy assuming interactions of 0. The y-axis here are the measured interactions at fixed coverage. So that's to say this y-axis is a fixed destabilization of the binding energy. So you can measure optimality because there's a theoretically calculated optimum of 1.6. You can say the optimality is just the distance from 1.6, right? So that's the binding minus the interaction. So you have this optimality, distance from optimum, where red is good and blue is bad. And then what you can do is plot a bunch of different things on this plot from the experiment. And let me go back. Sorry. Yes. So the first thing you can do is take the literature benchmark values that we previously measured using the low throughput system and plot them for two materials. The first is an amorphous iridium oxide, and the second is that same sample but has been annealed at 550 degrees for 4 hours to increase its crystallinity. This actually changes the color of the material, it changes a lot of its properties, it makes it go blue. So you move from here, it turns out you move a small amount in binding, not so much interaction. Now what we can do is do 3 high throughput campaigns. The sputtered plate I discussed earlier, and these exact samples made by the same first author of that previous paper. So if we run now high throughput campaigns on each of these 3, we see, first of all, the amorphous matches quite well. And this annealed sample, it matches well with some small error, which we think is a result of basically better data and better algorithms. And then finally, this sputtered plate. And so the first thing I think you can say is this is some proof that we have a benchmarkable means of extracting descriptors at scale, right? Because we can reproduce kind of carefully, experimentally measured things that require totally different assumption sets to extract. We use totally different sets of assumptions to extract these, and totally in comparison to the algorithm I discussed earlier. And then we have this plate, which is really interesting that it has a different property, right? And it basically is saying that preparation is making a difference to the activity of iridium. If you think about that strontium iridiate, the amorphous strontium iridiate, amorphous iridium oxide on the strontium iridiate, that's not surprising in a way because we know that there's a lot of literature now on these paracrystalline motifs, the medium range ordering and interactions of the structure of iridium oxide that can play a strong role in dictating performance. So yeah, you can really see this in the fundamental properties because this material is transparent, this material is midnight blue. And if you do XPS, you can really see the difference in the iridium oxidation. So you are genuinely changing fundamental properties. So I don't think it's unreasonable to think that we're tracking a change in fundamental properties that's driven by crystallinity. And that's really interesting because I think it basically says that we are able to keep track of something quite interesting. It's not using high throughput spectroscopy. We're able to kind of reduce our errors and produce statistically significant numbers, not just to do scale, but to do fundamental science. So we can start to really explore this space. And I think that's interesting because understanding how different materials populate this space might start to tell us about these interaction energies and also how much variance of performance this two-dimensional map really explains, right? Because this is still a gross simplification of electrocatalytic activity. So yeah, with that, I'd like to thank you all and finish up. Yeah, I'm happy to answer any questions.
Thank you very much for the very nice talk. It's very insightful. Obviously, a lot of advancement for the fundamental understanding. So for your combinatorial analysis and also the characteristic preparation, actually it is still it's very fundamental. It's easy to combine with the theory, but it's quite far from the realistic the system. Although you are considering the characteristic composition and also microenvironment, that is very well already controlled. Even maybe not use iron number that also hinders or changes microenvironment during the electrocatalysis. Right? So the descriptors obtained in your system is kind of something representing or is even comparable with a model like a discovered catalysis is also very important, the issues. So you might have some comment on that.
I absolutely do. I think this is really just a start. That's all it is just a start. I think we have to really build on this. Both theory and experiment are trying to expand to encompass complexity. How we do that is quite challenging. The advantage of this approach is that it can sample structural complexity of the surface, right? It can actually sample, so we have done ion incorporation of something like nickel oxyhydroxide. So it can sample and start to, this analysis, this algorithm alone is not enough, right? Because this algorithm is making a homogeneity assumption and an assumption in this high throughput work of populating. What I didn't say is that in the iridium oxide, we did a great deal of work proving that the intermediate we see is the rate limiting intermediate. So we proved if you open the circuit, watch the optical decay of that signal, you end up with 4, and then you measure at the same time the rate of O2 evolution. You find that the rate of O2 evolution is 4 times the optical decay of that signal. So that's a gold standard proof because we know the turnover frequency, we know it turns over, it generates oxygen, and we know there's enough composition, right? I think populating this space by making all of the gross assumptions and then seeing what fails is a very interesting way to start to understand the space of materials. Because we make the really bad assumptions knowing it's going to fall down, and then try and understand the failures. So something like nickel oxyhydroxide is a great example, right? You talked about ion incorporation, right? Well, there it's going to fall down because you have a subset of extremely active ion incorporated edges on an inactive basal plane. So it's not going to work. It's not going to work. But then understanding what we can and can't know. The final comment I'd have to say is no one technique gives you a complete picture. So this kind of expanding this will be interesting, but at the end of the day, operando spectroscopy, even as a field, say you could get high throughput Raman IR, in situ mass spectrometry at the same time as this, and laser-induced transient heating, there still wouldn't be enough, I think. We need to really expand.
So I have one more question. So just line with your answers. So you might have some plans to expand your study to a little different material definitely, and some other more complicated reactions. Especially I wonder you are also working on or have some plans to expand to the reactions where the product analysis that required during the in situ analysis.
Can you say that the last part again?
So for example, if you go to a CO2 conversion, for example, you need to really monitor the reaction product or intermediate reaction. So that could be a little more complicated. Designing the cell, but and if it combines, then you may have a lot of information out of it.
Yes, so the next generation, hopefully, of this instrument. So my group is actually not going to be fundamentally truly a fundamental electrochemistry group. It's primarily an instrument design group. The next generation of this instrument will combine this technique with laser-induced transient heating to find the point of zero charge at the same time as this. The final iteration will contain a Raman spectroscopy unit and in situ LCMS and ICP-MS. Because the point of designing this flow cell is that everything's on a defined flow path with peristaltic pumps pulling at the same time. So you can sample from the chamber. You can do in situ sampling from the chamber, and you can do end of run sampling from the chamber. So there's a few, so the idea would be, yes, run up the system, have the flow continually, backtrack the product, find the point of product generation and intermediate, see if we can see any intermediates coming off. Thank you. Thank you for your questions.
So thanks for all of engagement today. So Ben's talk was the last one that we prepared today. So this is the concluding remarks from the organizer. And hi again, my name is Sing-Jae Shin, and I'm the assistant professor in UNIST in the School of the Energy and Chemical Engineering. So actually this workshop was organized by myself, but it is PIs involved in this project. So from the registration side, I summarized this data. So I surveyed the online attendees or some in-person attendees. So many of them are from UNIST, and some of them are was from the KAIST in Daejeon, and so some of the attendees are from TGIS, and maybe they are from online. And those of all of I thank for every attendee here and online. And there must be some international attendees as well. And I surveyed another interesting one. So interestingly, half of the attendees are postdoc positions. So I was quite surprised. And I also surveyed of their research interest, and many of them are related to the hydrogen technology, and they must be interested in Ben's talk maybe. And some of them are related to the developing computational method and using AI for developing computational chemistry course maybe. And some parts of our attendees are from catalysis community, so they found many of interesting talk today. And some of them are from solar energy conversion, and some of them are from energy storage system, and some of them are from basic material science. And I also did some research about whether they do research about using AI or doing research on AI. And interestingly, very small part of them are not doing research with AI, and some of them are having plan to do some research in the future using AI or with related to some topics related to the AI. So this is the final slide that actually this workshop was fully supported by this Kaidro Studio InnoCORE research team, and I really appreciate Professor Song to support this workshop, and I also thank for other advisory professors, Jiu and Tae-hoon, and I also appreciate Myung-hee, and I really thank for Chaewon for her contribution to have all of our invited speakers to be well settled today. So thank you for your attention, and I really look forward to seeing you in the future in UNIST as well. Thank you.